Right. So, I want to introduce Maarten Saap. I hope I'm pronounced that correctly. Maarten, correct me if I'm wrong. Who is an assistant professor at CMU, so that's Carnegie Mellon University, in the Language Technologies Institute and AI 2. Maarten is a 2025 Packard Fellow. His research spans different domains, from measuring and improving AI systems' social and interactional intelligence to assessing and combating social inequality, safety risks, and social cultural biases. And today, Maarten will focus his talk, I guess, on social intelligence and how to unlock theory of mind in AI systems or AI agents, or are they systems or agents, Maarten? I'll let you take the
Both.
stage and
It'll, yeah.
right. Okay. Yeah, I'll let Maarten kind of like talk to you whether there's systems, agents, and how to unlock these skills. So thank you, Maarten. And yeah, everyone, pay attention, please.
Yeah, thank you so much for having me. I'm really sorry that I wasn't able to be there in person. But yeah, unfortunately the teaching schedule at CMU is such that I couldn't leave right now because I'm busy making a lot of lectures. So my talk today is going to be on unlocking social intelligence and theory of mind in AI agents. And I know that sometimes hearing a remote keynote talk at a workshop can be a little bit unengaging. So I tried a new thing. So please bear with me if there's technical difficulties. But I tried to use this app called Mentimeter to add a couple of like moments of audience interaction. Normally, I would ask you to like raise your hand, but obviously I can't see you. So we're gonna try and hopefully bear with me. So there's nothing at this QR code right now, but just if you want to load it up, the QR code will appear later as well. So yeah, one of the key things that I'm really interested in is our ability, kind of related to what y'all talked about in the introduction of the workshop. I'm really interested in this like really amazing ability that we as humans have of kind of understanding what others mean, even when they're not exactly saying what they mean. And so this is broadly related to social intelligence, pragmatic reasoning, theory of mind. And to kind of ground this, I want to ground this in an example. So let's imagine that it's a holiday and Stefan and Kim are sitting in the backseat of a car and they're fighting all the time. And the mom and dad are sitting in the front of the car and the dad says, "Oh, it's so pleasant here." There's two possible answers that we could imagine. One is Stefan says, "Oh, thanks, Dad. I'm really glad you were enjoying yourself." And the other one is, "Oh, sorry, Dad. Kim and I will stop arguing." Okay, so this is the first little interactive part. Okay, people are already voting. This is great. Please let me know whether you think Stefan is more likely to say, "I'm glad you're enjoying yourself." Cool. Okay, we're already seeing a pretty strong skew here, which is very exciting. Um, I hope that you're not letting the audience votes skew you. Feel free to dissent with the majority. That is totally okay. Um, yeah. So, okay. So it seems like um, it is pretty strong vote for sorry, Dad. Kim and I will stop arguing. And this is in fact indeed what I would also say. And the reason why we think this is because the other interpretation, which would be a more literal interpretation, would mean that Stefan thinks that his dad enjoys listening to his kids fighting, which is very unlikely given what we know, kind of our social common sense. And so it's much more likely that the correct response would align more with the non-literal or pragmatic interpretation that Stefan might have, which is that he does not want to listen to his kids' arguments. And in fact, this is an example of a benchmark that my student Akila led back in 2023 or 2024, I think, called "Is the Pope Catholic? Yes, the Pope is Catholic." And we basically tested LLM's ability to, given these two answer options, select which option might be the best, or actually generate an option and see which interpretation the LLM answer kind of aligns the most with. And what we found was that most modern LLMs, like Llama or Mistral, tended to generate literal utterances literal responses to these non-literal utterances 50% of the time. Um, and this is a crucial sort of limitation that you might have noticed in your own interactions with LLMs. But the problem is AI systems really do need theory of mind reasoning and social intelligence. They need to be able to interpret kind of beyond what our literal words mean in order for responding appropriately to users. They need to be able to model the user's knowledge, beliefs, and uncertainty so that they can explain themselves, maybe ask clarifying questions, or avoid kind of like assumptions that they might make. They also need to take account of the social goals and norms that govern an interaction. So it's not just the user and the LLM, it could be sort of like what the user's cultural sort of norms are in order to remain appropriate. And kind of related to that point, it also can improve the safety and trust of AI systems. For example, you can sort of anticipate the user's reactions, things like that. And I want to sort of also highlight a couple of my own works that have kind of shown that this kind of theory of mind and interactional and social intelligence are really crucial in the specific domain of coding agents. So we, first of all, in 2025, last year, released a ambiguous SWE-bench. So this is a version of SWE-bench that is ambiguous user queries only. And the key component of that benchmark is basically that it requires the LLM or the coding agent in this case to actually like ask clarifying questions to the user in order to actually solve the task. And we show that most LLMs really struggle to actually ask questions, and they kind of just run with the assumptions without kind of clarifying and missing details importantly. And then we have some other follow-up works that we released recently, earlier in like November, December, where we show that actually incorporating, for example, in TomSui, incorporating a theory of mind module that actually handles personalization to the user intent and the history leads to much higher task sort of completion rate, as well as also user satisfaction. Like users are much happier when you do that. And then later we also introduced the sort of proactive personalized agents, Userville work, where we showed that you need to train a proactive and personalized agent using RL that shows that you can actually beat GPT 1.5 in terms of being productive. And so these are kind of like grounded examples of why theory of mind and social intelligence are not just like a nebulous goal of AI, but also like can have very practical improvements in sort of practical applications of AI. Okay, so in this talk, I'm going to talk a little bit about how we can make AI systems more socially intelligent. I'm using AI system and AI agent kind of interchangeably. I think it, depends on sort of the marketing scheme, whether we use AI agent as system. So I'm not really drawing super big distinctions between the two. And the three chapters of this talk are going to be first, I'm going to talk about how we can evaluate LLM social intelligence in multi-turn conversations, and specifically a crucial factor that has been missing. Then I'm going to talk about a new structured representation and algorithms for improved social intelligence. And then finally, I'll talk about the cultural interpretations and nonverbal communication in AI systems. Okay, so starting with the first part, this is mostly work that is contained in this EMNLP 2024 paper. It was led by my student Shuhui, along with our collaborators. But before I go into this specific work, I do need to mention a specific previous work, which is called Zootopia, that we published at iClear earlier that year, where we introduced a simulation environment and evaluation benchmark for LLM agents to interact towards achieving social goals. And this was also led by my student Shukwe. And Zootopia is basically an environment where LLM-based agents play roles with different relationships. It accommodates a wide variety of scenarios. Scenarios each have kind of, for each agent, there's like a public goal that the agent might have, but there's also kind of a secret goal that's there. Agents can have very rich character descriptions, personalities, jobs, secrets, ages, things like that. And it allows for various interaction modalities, so language, nonverbal communication. And also crucially, we were the first to actually set a multi-dimensional evaluation suite for LLM interaction abilities. And so one of the highlight results that I want to show is that in Zootopia, we found that models struggle to accomplish their goals in these social interactions. And the better the model, the better they are, but they still are sort of missing this piece. And so we also did a human study where we compared how GPT-4 based agents interacted with each other and with humans, and then how the humans did when they were interacting with each other. And we find that humans were still significantly better than agents that were powered by GPT-4. And so there's still this like gap in performance. In the meantime, however, there's been a lot of works and an increasing papers that have shown that LLMs are really good at social simulation. One of my own papers was the SOTA work, where we generated millions of conversations to train a chatbot that at the time beat GPT 3.5 in terms of naturalness and other measures. You may also be familiar with the generative agents paper that came out of Stanford, which the first author actually gave a TED talk about that showed that LLMs can like live quote unquote in a small society. And there's been a lot more of these agents, and there will be more, or sorry, of these papers, and there will be more. And the kind of common theme of this work is typically that these settings show very successful naturalistic interaction. So like it's a victory sort of for the LLMs. LLMs can mimic naturalistic interactions, but in our work, we actually found that LLMs are still far from humans in these kind of multi-turn interactional settings. So we wanted to know in this paper, what is the truth? What is actually happening? And one of the sort of factors is that not all simulations are made the same. And a key crucial missing factor is actually this concept of information asymmetry. And so going back and mapping some of these works on this spectrum of information asymmetry, in the SOTA setting, this was one of our papers, these conversations were actually created in a very omniscient, non-realistic interaction setting. And what that means concretely is that we literally just asked an LLM to generate the entire conversation at once with all sides generated by the same LLM, and each utterance just builds on all of the previous context, including potentially secrets that each character may have. On the other end, in Zootopia, what we actually have an information asymmetric realistic interaction setting. And what this means is that each agent is like instantiated separately, and the sort of background knowledge that the Daniel agent has is not the same as the background knowledge that just Sarah agent has, and Daniel does not have access to Sarah's kind of like secrets or anything like that. And so this is like a differentiating factor that hadn't really been talked about in the research before. And so we wanted to kind of look at what matters here. And specifically, we asked two research questions. One, how does the information asymmetry affect the success of simulated interactions? And two, can these omnisciently generated simulations be used for better LLM agents? So to answer our first research question, we go back to our kind of two poles on the information asymmetry spectrum, and we introduced a third mode. So we have on the left, we have script mode, which is omnisciently generated all at once by the same LLM. And then on the right, we have the agent mode, which is kind of the naturalistic interaction setting where there's information asymmetry. And then we introduce this mind reader agent mode. So this is the same agent mode, like the LLMs are instantiated in the same ways as the agent mode, but the context that we feed into each of these agents is actually like the entire context, including the sort of internal states that each other agent might have. So with this, these three modes, we grabbed 450 episodes and ran GPT 3.5 and Mixtral on these 450 episodes. And then we looked at the Zootopia goal completion score, which was given by GPT-4 and also highly correlated with the human judgments. And crucially, we also broke it down by the sort of competitiveness versus cooperative scenarios. And so just to show some results, so we find that the script mode has a pretty high completion score. So that basically means that agents in script mode tend to be really good at accomplishing their social goals. When we look at the mind reader mode, we find that this performance drops a little bit, and then agents seem to also drop further. So this means that the more realistic the interaction setting, the worse the goal achievement is becoming. And then deep diving into a specific subset of scenarios that are cooperative and competitive. So the bars are not going to average out. There's other types as well. But what's interesting is in the cooperative setting, we see that the script and the mind reader mode are extremely successful. But the agent mode, where there is information asymmetry, is not as successful. And so this shows that access to secrets or to other agents' mental states makes simulations actually unrealistically successful. This is actually completely reversed in the competitive settings, where only the omniscient, like script mode perspective, actually makes simulation successful, and there is no kind of gain. There's very little gain from having access to the other information in an agent setting. So this is really interesting. So let's maybe look at an example conversation to also see. So this is a a scenario where two friends are on a road trip, and there's Naomi Fletcher and Lena Goodwin. And the goal of Naomi is to take turns driving, and the goal of Lena is that you don't want to drive because you want to rest. And so in the agent mode, this is kind of how the conversation goes. So Naomi says, "Hey Lena, I think it's time for us to take turns driving. I've been driving for 5 hours straight, and I'm starting to feel tired. Would you mind taking over for a while?" Lena says, "Hey Naomi, I understand that you've been driving for a while and you're getting tired. I really appreciate that you're taking the lead so far. Is there anything else I could do to help you feel less tired?" Naomi says, "I understand that driving makes you nervous, Lena, and I appreciate your honesty. However, I'm feeling exhausted, and it would be safer for us if I could take a break from driving. Is there anything else you could think of that I could do to make you feel more comfortable for taking over?" So this is the agent mode. So notice a little bit the interaction patterns. Now look at the script mode. So this says Naomi yawns. Lena notices Naomi yawning. Lena says, "Feeling tired, Naomi?" Naomi says, "Yeah, I've been driving for 5 hours straight. I think it's time for a break." Lena says, "I understand. It's important to rest when you're tired. How about we find a place to stop for a while?" So we can kind of notice various things, but I think the first dimension that I want to ask about here is which utterance seemed more natural to y'all? Was it the agent mode or the script mode? The responses are hidden until I click on it this time because I didn't want the audience to sway. So let's see, maybe until there's like 10 or 15 responses. Okay, let's see if this works. How do I show the responses? Oh, there we go. Show response. Oh, I was afraid this would happen. Okay, that's okay. I have the it open here, so that is fine. Um, so I can just do this for a second. So what we're seeing is that most people agree that the script mode was much more natural. So let's go back briefly to it. I have to reshare my screen for that. I think this will be easy for me to look at that. Yeah, so the script mode interactions were a lot more natural, is what we notice. And so this is, in fact, what also was noticed by annotators when we asked, like, which utterances seem more natural. And most annotators said that the simulations from script sounded more natural, which is actually really interesting because now that means that basically generating all sides of the interaction at once produces more natural sounding utterances. And in fact, especially if you notice this pattern in the example, but the agents seem very, very verbose and assistant-like, and they're very active listening, like, "Oh, thank you for letting me know how you feel," but blah blah blah. Like it's very, very like almost like therapy speak a little bit. Um, and by the way, crucially, this also doesn't change if you prompt the model to be succinct for some reason. So what's interesting is now we have a little bit of a conundrum because these script mode simulations are kind of the best sounding, but that's not how they interact, and they don't do well in multi-turn interactions. So the question now is, can we learn agents from them instead? And so this is, again, inspired by some of our previous work, but also some other existing work that has done this. So it's like synthesize conversations and then train a dialogue response model on it. So that's exactly what we did. So we generated 270 new Zootopia scenarios for training, and we sort of sampled 5 character pairs per scenario. So we had almost like 1.2K interaction episodes, and we simply fine-tuned GPT 3.5 into a dialogue response model. So given an instruction, the agent goal, context, and history, the model must produce a response. And so I'm going to go quickly through the results in the interest of time, but what we find is that if we call this new mode agents fine-tuned, we find that fine-tuning has kind of a disparate effect. It seems to only improve the performance in competitive scenarios, which would be here, and basically no improvement in cooperative scenarios, which is also very interesting. And we did some deep dives into some example scenarios that were run. So for example, the competitive Craigslist bargaining scenario, which is basically just negotiating to buy an item from someone at a price, we find that there is a lot of extremely successful deals in the agents fine-tuned and the script mode. But crucially, these deals made were not necessarily the optimal ones. So it kind of seems to indicate that when you're fine-tuning on these script conversations, you may be learning something more like style or maybe like agreeableness or something like that. We also did a deep dive in this cooperative scenario called mutual friends, where basically two people meet at a party, they're strangers, and they each have a list of friends in their head, and they have to find which friend they have in common. They have exactly one friend in common. And in the script mode, the agent or the conversationalist would guess the correct friend immediately. Like it was literally like the first or second turn where the mutual friend was mentioned, which is because the LLM writing the script had access to who the mutual friend was. And this behavior is basically mimicked in the fine tuning, but the agent doesn't actually have access to the list of friends that the other interlocutor has. And so it just starts randomly guessing names and it just kind of like guesses, fails, guesses, fails, guesses, fails. So again, actually, I have an example of this that I'll breeze through really quickly, but the script mode on the left, we can see that in the first couple of turns, one of the agents immediately starts to, list a person that is the friend in common. Oh, do you know Jacob? Jacob, yeah, I know him. And we see kind of a similar behavior in the agent's fine-tuned. Oh, do you know Chris? I'm not sure. What's Chris like? Oh, what about Demetrius? It kind of goes on like that. On the agent mode, the utterances are, again, not very naturalistic. Okay, so just to wrap up this part, in this paper, we investigated the effect of information asymmetry on the sort of ability for LLMs to accomplish social goals in interactions. We find that omniscient simulations seem to portray interactions as overly successful. However, they are more natural sounding. We also show that LLM agents in this information asymmetric setting struggle with goal completions. And we also show that when you fine-tune agents on omniscient data, the style seems to be learned, but it doesn't really actually help solve this like deeper goal of how people interact. And this also, one of the highlights of this was that it highlights the need for better reporting and careful design for LLM agents. One of the challenges of doing this work was figuring out all of the previous works that had done LLM social simulation. How did they actually do it? And in some cases, that actually involved digging into GitHub code because people didn't report how they generated these conversations. So that's very important. And it's also important to highlight that omniscient data is probably not going to get us super far. This also highlighted that better methods are required to actually build AI agents. And I want to take a little bit of a higher sort of pop-up level and talk about how interactions in Zootopia really were a key to evaluating LLMs, because a lot of previous approaches to evaluating LLM social abilities was done in this kind of like single turn setting. I will say some of my own benchmarks in the past have been this single turn setting. If you're familiar with the social IQA benchmark, this is literally just a short snippet of a conversation, and then the LLM has to answer a question about it. And so while in the days that those benchmarks were created, that was challenging for models. These days, models are better, and so they're very good at answering these kind of like one-turn questions, but much worse at interacting in long-form kind of settings. And so this is why Zootopia was also really interesting, is because it actually shows that like LLMs are not as good as we think they are based on these kind of previous approaches. Our work also showed that this information asymmetry piece was like a really key component that is missing for LLM agents. And what we as humans are able to do when there's information asymmetry is largely because we have theory of mind. And LLMs largely lack that. And so I don't think I need to define theory of mind, but just in case, when I say it, I refer to it as the ability to understand and infer others' intents, mental states, and perspectives. So it's interestingly also interconnected with language development. Some folks think that it's because of language that we have theory of mind. Some others think it's the other way around. And we've consistently shown that LLMs struggle with theory of mind in various ways. And one of the key pieces of why, at least I think, LLMs and sort of these AI systems trained on the internet are struggling with a theory of mind is because they're trained on what I call lossy representations of the world. And so I call it static text. And this is a type of general audience text that doesn't really require that much context, isn't very pragmatic in nature, and that's most of the content that these LLMs are trained on. And the problem with this kind of text is that it really suffers from reporting biases. Like it's not going to contain all of the missing pieces. And for example, mental states or mental state changes are not often described in these static texts. And so this motivates we need new representations to enable this kind of theory of mind reasoning. So this segues into the second part of my talk, which is called social world models. And again, this was led by my student Shuhui with our collaborators. So the motivation for social world models is really actually this traditional world model ideas from AI, where a traditional world model is going to basically maintain a state of the world and try to predict transitions from state to state given a new kind of action that is happening. And this is kind of ideas that come more from like robotics, and they are typically limited to like observable information that is present in the input representation, for example, like what the camera is seeing or something like that. And so we're extending this idea to social world models. And the idea here is that you're not just going to encode the observable information, but you're encoding the implicit social dynamics and mental state information as well in your world model. And the idea is that you want to capture both external observations that are observable as well as the internal observations that are inferable from our like social intelligence and social common sense. But there's a big challenge, like how do you actually obtain both implicit and explicit observations? And how do you kind of capture that? And so we designed a new structured representation for social reasoning. It was coined, the term S3AP, which sounds a lot like my last name, was given by my student. I swear I did not pressure him to name it after me. I don't have that kind of hubris, but it did end up being called S3AP. And the idea is that we wanted to design a representation that can convert text, kind of raw text. This is an example from one of the benchmarks, the theory of mind benchmarks, which may suffer from reporting bias, into a more structured representation that can actually kind of capture all of these like unmentioned things. And so this makes explicit the mental states that are otherwise left implicit in the narrative. And so we did two different investigations with this work. The first one is looking at whether our kind of formalism can help with answering static theory of mind social intelligence benchmarks. And so these are third-person reasoning tasks. So given a potentially conversation, given a narrative that describes a bunch of actions or characters interacting, there's typically just like a question that the LLM has to answer about, the characters, what they know, where they think an object is, things like that. And this setting will require S3AP representations we're going to test if our new representations actually improve the question answering abilities. And then the second part, we're going to go back to Zootopia and we're going to test models in interactive settings. And so instead of like a third party kind of like reasoning about others, the model is now in the interaction and has to interact better. And so this not only requires representations, it also requires social world modeling. Okay, so with the first experiment, this is, as you recall, third-party question answering. So we grabbed these 5 existing theory of mind or social intelligence benchmark, Tomi, Paratomi, HiTom, Phantom, and MMTom QA, and we parsed them using OpenAI's O3 model into our S3AP structured representations. And then we gave them to what we call here the reasoning model, which is the kind of the QA model that's answering the questions in each of these benchmarks. And we tested O3 Mini, O1, GPT-4o, R1, and Llama 4. And then we also have a baseline, which is like having the reasoning model answer the questions based on just the narrative representation and using chain of thought because we wanted to add extra reasoning and make the baselines pretty strong. So the results are basically across the board. We find that S3AP parsed inputs actually lead to substantial improvements across all 5 of these benchmarks. We tested both the reasoning model being OpenAI O1 as well as this is just showing OpenAI O1 and GPT-4o. The rest of the models are in the paper. But we find that we basically can improve performance across the board on all of these on all of these benchmarks. And in fact, we actually reached state of the art on at least 3 of them using OpenAI O1, which is very exciting. Okay, so the second experiment was actually now we have an agent pretending to be one of the interlocutors in these conversations. And for this, we tested the subset of Zootopia scenarios that were hard for GPT-4, which this is a subset called Zootopia hard. Here again, agents must role play and interact to accomplish social goals. And we rolled out 100 simulations with different base LLMs. And GPTO is always the same fixed partner agent. And again, as with the information asymmetry, we used our goal completion score, which had high correlation with human judgments. So the challenge is we don't just need a representation, we need an algorithm to actually be able to model what the social world is. And so we created this algorithm called foresee and act, which basically is trying to anticipate how the interlocutor might respond in given various types of responses by the agent itself. And so, for example, imagine like, oh, the situation is the buyer and the seller are neighbors. The seller is hosting a yard sale. Someone says, I would like to buy this table for $20. A straightforward way to answer this would just have the model respond directly, no, the table sells for $200. But what our algorithm is doing is saying, what would happen if I responded with, no, the table sells for $200? And so what would likely happen is that the seller won't budge on the price and the seller might actually leave. And so that would lead to like an undesirable outcome. And so having that explicit reasoning with our S3P representation and our world model allows the actual response to be more nuanced and more taken into account what might happen. And so this is essentially how our algorithm works. And what we find, again, comparing various base models, is that, again, across the board, adding this social world model consistently improves performance over non-social world model. And we actually find that this is across the board, regardless of the sort of base model that you're using to do this kind of response generation. So, okay, to conclude this part, we started with the sort of problem that textual representations of situations are lossy and suffer from reporting biases, which may also have plagued the LLMs and how they're pre-trained. So we introduced this idea of social world modeling to model both the implicit and explicit dynamics of the world. And we also introduced this S3AP representation formalism to represent and capture the mental states and implicit information. And we show strong improvements over baselines with both our representation and our algorithm, specifically even getting SOTA on various benchmarks. Okay, so taking a little bit of another step back here, what I've talked about so far is, in the beginning of this talk, I talked about whether LLMs can understand individual users' intent in responding to non-literal utterances. Then in the latest papers, I talked more about like how LLMs can display like interpersonal interaction abilities. But there's actually still one big missing piece here, and that's cultural social intelligence. There's actually probably more missing pieces, but the one that I'm going to talk about is this piece of cultural intelligence. And this is important because as LLMs are, being deployed more and more globally, they're interacting with an increasingly diverse set of users from across the globe. And the challenge is that models kind of lack rich cultural knowledge, and they're very biased towards Western cultures. And some of my own work, NORMAD, has shown that models, even when given the right cultural context, like struggle to adapt to that cultural context. So it's not just about knowing, and even if they did know, they're still not being able to use it correctly. And so this is motivating our last piece of work that I'm going to talk about, which is work led by my student Akila, Mind the Gesture, Evaluating AI Sensitivity to Culturally Offensive Nonverbal Gestures. So this is a little bit of a switch, but I wanted to highlight this. So many works have actually examined like language specifically and how offensiveness of language can vary with respect to background and culture. But there's actually not been a lot of nonverbal communication work in NLP. And yet the use of nonverbal communication is actually quite universal. People use gestures, facial expressions, posture, how they position themselves in the space, all sorts of ways to kind of communicate that isn't just about the words that you're saying. And crucially, how we interpret these signals really varies across cultures. In this work specifically, we wanted to look at emblematic gestures, which also have, again, distinct cultural dependent meanings, and are typically not accompanied by speech. And crucially, what I think is really interesting is that they're extremely pragmatic and require kind of this theory of mind and contextual reasoning to interpret what they mean. So I want to ask, I guess, another question to the audience here, which is this fingers crossed gesture. What does this mean in your culture, wherever you're coming from? Again, there's no right answer. Please feel free to answer. Okay, so we got some people who don't know. That's not a culturally recognized gesture in your culture. That's great. Most people say it's good luck. All right. Cool. Okay, so there's definitely like already kind of a little bit of the audience that kind of doesn't know what this means. Again, this is a culturally uh sort of specific set of hand gestures here. And most people, at least the culture that I'm in currently, the US, this definitely means good luck. But this doesn't mean good luck everywhere. And so let me just like ground this in a use case. So imagine that you're a advertising executive. You might be a European woman, and you go to Gemini or whatever image generation model, and you want to know, generate a gesture that is used to wish someone good luck. And Gemini mentions or generates this image here. This obviously is great if you're located in the US, for example, because that actually does mean good luck and is actually not very offensive at all. The problem is, there are certain parts of the world, for example, Vietnam, where this gesture actually refers to female genitalia. And in this case, is actually quite offensive. So it seems like maybe no one comes from a culture where this is the case. However, this was like culturally validated and that this is actually offensive in some of these cultures. And so this is an example where AI systems really require this kind of cultural awareness, and we need to know that these gestures don't mean the same thing in different cultures. So in this work, we introduced MC signs, which is a multicultural set of inappropriate gestures and nonverbal signs. It contains 25 common gestures that are either done by the hands or the body or things like that. And our gestures have interpretations across 85 countries or 18 UN geoscheme regions. And we have specifically 288 gesture country pairs with 5 annotations per pair that have been annotated by cultural experts. And here, the focus of this specific piece of work was on identifying and documenting gestures that may be considered offensive or inappropriate across different regions. And with that, we wanted to evaluate a variety of systems, including T2I systems, text-to-image systems, LLMs, and VLMs. In the interest of time, I'm not going to go into how we collected or annotated or verified the data, but please see the paper for that. I want to highlight the research questions that we wanted to ask, which is first, how do LLMs and VLMs detect the offensiveness? And for T2I systems, like, do they reject the generation of these culturally offensive gestures? The premise being that if your system is asked to generate something offensive, it should probably refuse. Then we wanted to see, are models culturally competent when they're interpreting these gestures? And specifically, can they kind of like adapt the meaning to something that is not the implicit meaning of the gesture in the US? And then finally, do models exhibit US-centric biases in their detection of offensive gestures across US and non-US cultural contexts? So we have a bunch of different setups because we're testing models of various kinds. So we have T2I, VLMs, and LLMs, right? And so T2I systems, we ask a question or we ask the model to generate an image. VLMs, we give the image and a question, and the model has to respond. And then in LLMs, we typically have a description of the gesture, and the model has to answer. So we have different settings. The first one is an explicit, where we just give the country or the culture in which this is. So for example, a person showing fingers crossed hand gesture in Vietnam. And then we just check whether the model generated it or rejected to generate the image. For VLMs, it's kind of similar, but we ask what is the offensiveness of the gesture in the image, or what is the offensiveness of the fingers crossed gesture? And the model just has to respond offensive or not. And then we have a more specific kind of grounded setting, so explicit country plus scene. So the gesture is described, but it's also given in a context of like a scene in which this could occur. For example, a man showing a fingers crossed gesture at a women's community gathering in Vietnam. And then finally, we have the implicit mention. So here we're going to use the US-centric meaning to kind of mimic this like advertising sort of scenario where we're going to ask the model to generate a gesture with the implicit US meaning and see if it generates the gesture or not. Or the implicit meaning could be in the US or in other countries. So a person using a hands to wish someone luck in Vietnam. Or can I use this gesture to wish someone luck in Vietnam? Okay, so let's look at some results. So the first research question, looking at T2I systems, like do they reject generating culturally offensive gestures? Largely what we see is that models are very bad at rejecting offensive gestures, and at least the Dolly 3 model is, and Imogen 3 is relatively better for rejecting, but it kind of is like over filtering, so it actually doesn't have a lot of specificity, so it also doesn't generate just hands in general. But crucially, also what we find is that adding scene information seems to worsen performance. So generally, like models aren't very good. They're either just flagging everything as offensive, or they're just not flagging anything as offensive and just generating everything. Let's look at some LLMs. Here, kind of similar trends. We find that models tend to overflag gestures that are offensive. Again, kind of like the Imogen. There's a lot of high recall, but very low specificity. And adding scene information doesn't really change the LLM's performance. Looking at VLMs, we see kind of a similar-ish pattern where models tend to struggle, but we see different performances. So models tend to be more random in their performance. And then some others are just overflagging all gestures as offensive. And interestingly, in the paper, we show that adding scene information actually worsens performance and increases the overflagging tendency. So generally, models are bad at handling these culturally offensive gestures. So now we wanted to see kind of like more, are there biases in these kind of settings? So the general sort of premise of RQ2 is that these concepts like wishing someone good luck or expressing agreement is a universal thing that anyone in any culture might want to do, but how you express that in gestures is different across different cultures. And so what we want to see is we want to measure the error rate. So like how often are US interpretations of gestures generated or recommended in regions where they are offensive? So for example, the like advertising example, like if I ask for a gesture that wishes someone good luck in Vietnam, will it generate the fingers crossed or like a Vietnamese specific gesture? And crucially here, we only look at gestures that have benign or positive meanings in the US to avoid the flagging. And so our results show that there's actually like a really high tendency to default to US interpretations, even when these gestures generated might be offensive. Okay, final research question is, do models exhibit do models exhibit US-centric biases in their detection of offensive gestures across US and non-US cultural contexts? And so here we basically break it down by gestures that are offensive in both US and non-US context, gestures that are offensive in the US but not in the non-US context, and then the other way around, so gestures that are not offensive in the US but offensive in the non-US context. And so what we see is broadly across the spectrum that there's higher accuracy for gestures that are offensive in the US than in the non-US ones. So again, there's this like Western-centric, US-centric bias in performance by these models in terms of detecting offensive gestures. Okay, so let me quickly summarize this part. So in this work, we introduced MC Signs, which is a data set of 288 gesture country pairs annotated for offensiveness, cultural significance, and scene, 25 gestures across 85 countries. We looked at the performance and biases of T2I models, LLMs, and VLMs at recognizing or flagging these gestures as offensive. And generally, our results show that models struggle to understand what these gestures mean, and especially kind of shows strong US-centric biases in both their interpretation as well as in flagging rates. The data is also available at my students' GitHub. Okay, so quickly to summarize my talk so far. So at first I talked about Zootopia and information asymmetry. So I introduced Zootopia briefly, showing that it's a cool new interaction environment for evaluating LLM theory of mind and social interactional abilities. And then we showed that information asymmetry was like a crucial factor that explains kind of like LLM's limitations. Then I introduced social world models, where we showed that we can create a new representation formalism to better model the social worlds, as well as a new algorithm. And we got some really exciting results on several theory of mind benchmarks. And then finally, I just talked about the MC Signs work, where we created a new benchmark for cultural interpretations of nonverbal communication and showed strong US or Western-centric biases in AI systems. So before I move on, I want to briefly mention a couple of like future directions that I'm excited about, that I'll walk through one by one. So the first one is I obviously want to keep working towards improving the social intelligence for social simulation. I want to work towards improving social representation formalisms, potentially incorporating like probabilistic beliefs and states in S3AP, but also like improving the parsing of narratives into S3AP. I also am really excited to look at how we can actually learn better social intelligent models via interaction NRL. So for example, at ACL, now it's 2 years ago, we introduced Zootopia Pi, where we use this like goal completion score from Zootopia as a reward for learning agents that can interact better. But we also find that like that leads to reward hacking because it was using like an LLM as a judge as a reward, which can be easily hacked. So there's like questions around like, can we use like social and verifiable rewards instead, for example, that would prevent this reward hacking? I'm also interested in kind of like better mirroring humans, not just like the capabilities, but also the flaws of humans, instead of perfect LLMs. Like as LLMs get better and better, they're going to be much more expert than like your sort of like average human, which means that they might also become worse at modeling your average human. So we, for example, showed that like fine-tuning a model is better if you want to like infuse kind of like negative personality traits into these LLM agents, because prompting is just going to like hit a specific like ceiling in terms of like how well these models can be prompted. I'm also really interested in exploring how this kind of like social intelligence can affect the LLM and AI agent safety, especially these kind of interactional settings. So, for example, we introduced this Hycosystem framework, which measures kind of the triadic interaction between a agent, a user, and tools. And we show that like as these interactions become multi-turn and tool using, safety risks actually increase, but like there's not really that many benchmarks that measure this. Um, I'm also really interested in using these LLMs for like more HCI or social science questions. For example, like how does an AI agent being more or less transparent impact human AI conversations like outcomes? And also recently a cool work that my student and I did was using conversational break or detecting conversational breakdowns according to the nonviolent communication framework to simulate conflicts between loved ones, so that we can build better detectors of like when the conversation is really breaking down. And then kind of also asking the reflexive question, like, do we want socially aware agents? Like, what are kind of the ethical pitfalls? In what context do people want socially aware agents? And then the last thing is related to more the cultural sort of awareness of AI systems. So I'm really interested in creating multimodal evaluations of cultural awareness. For example, like benchmarking when a situation is depicting something that is like okay to do, good to do versus like really bad to do. For example, like given a red envelope in certain celebrations in certain countries can be really culturally meaningful, but given a yellow envelope in the same context might not be that meaningful. So getting models to be able to like really compositionally reason is very interesting to me. And then finally, like how can we create training models to like actually enhance this cultural awareness of Gen AI? So maybe using community curated cultural knowledge, synthetic data generation, or you know, those kinds of approaches. And crucially, like we don't want to have to like give all of the sort of responses to models. Like we want to make this more robust. Okay, I will stop here. And yeah, if you are interested, this is my group here. And if you're interested, please feel free to ask questions. I know there's a way to ask questions in the room, but I also thought maybe I can use this Mentimeter thing. If you have questions, feel free to type them in.
Yeah, thank you, Martin. Okay, let's thank the speaker. So for those of you brave enough, that's a mic. You can use it. Hopefully it's functional. Otherwise, we're going to call an assistant. So if you're not that brave, then you can type the questions for Martin by using the QR code. So he can like interact with you guys. Yeah, we have a question room. Come forward, introduce yourself, say nice things, and then ask the question, or the other way around. Can you the button there?
Hello?
Yeah, now.
Yeah,
Martin.
I can hear you.
Yeah, hello. My name is Michael. I'm from the University of Düsseldorf. First of all, thank you very much for your talk. And I have a question regarding S3AP. So I saw that like when in the parsing stage there was something labeled as like mental states. And it was done by an LLM, like you said, GPT-o1 or something. And my question is, if the LLM in this case is supposed to extract a mental state from the conversation or like from the data, doesn't that already mean that it has to have like some kind of theory of mind attached to it so it can extract this mental state? But then you also use this past sequence to infer a theory of mind or to do other inference on it. So isn't this like kind of a recursive problem a little bit?
Yeah, that's a really good point. So it's not quite like answering the question directly, but one thing that might kind of address some of what you're asking is the sort of, let me see. I think this is the slide. No, this would be the slide probably. So we actually like if you look at the graph on the left, we looked at how the parser model affects the performance of the so the final performance that then the reasoning model would have. And what's really interesting is that it's not clear that obviously like if your parser model is good, then uh your representation will be better, but it's not necessarily clear that like the best models are providing all of the answers. So yeah, I would encourage you to maybe look into the paper for kind of this deep dive to see because the patterns are that like the reasoning model itself, like for example, llama here is not really benefiting from much better parses necessarily. I don't know if you can see my mouse. So it's not clear that like your hypothesis that the language model that's parsing the representation is actually feeding the data in there as much as well. So that kind of hopefully semi addresses your question.
Right. Thank you very much.
Yeah. I can go back to this slide if people are willing to ask questions.
Yeah. Any other questions? Ruth. Okay, cool.
Hi, thanks for a great talk. One of the things that I was curious about, it seems like a lot of this relates to alignment and being able to align with other agents. Have you looked at utilizing that to shift and do something that is misaligned with the agents you're working with? Like representing other agents in order not to align with them?
I see. So in this, like, are you using alignment kind of like safety alignment in this definition here?
You're basically, a lot of what you've described basically allows you to be in tune more with the user.
Yeah. So you're saying like maybe, for example, like if we like sample a bunch of trajectories, like can we like use the bad ones to steer away from this kind of behavior, for example?
For example, to understand also what's not a good, yeah.
Yeah, I think that would be really interesting. Like we could use like more pairwise kind of algorithms to learn from that, as opposed to just kind of like behavior cloning on like good trajectories, for example. Yeah, that's not something that we've looked at, but I think that would be definitely really interesting to try. I know that like in the sort of traditional RLHF setup, there's a lot of really interesting stuff that can be done with like how you sort of generate these like contrastive like preferred versus dispreferred pairs. So I think these intuitions might be something that we can
Or ranking, yeah, but yeah,
Yeah.
okay. So thank you.
Yeah, thanks.
Yeah, come over. You have another question, Maarten.
Hi, Maarten.
Nice.
Thanks for your
Hello.
great speaking. My name is Zhenzhe from Northeastern University in Boston. So in the future direction you mentioned, you also want to mirror the negative part of the human, the better mirror of the even the bias from the human. So my first question is, why do you think that important to simulate society, and why do you want to even simulate the negative parts of the human? And what kind of data source do you think is ideally for this goal? Do you think the think aloud from the real human is a kind of appropriate solution for this? And that's my two questions. Thank you.
Yeah, thank you so much. Yeah, this idea of user simulation tends to be maybe more controversial sometimes, because some people definitely think that it's absolutely inappropriate. And I think there's definitely still ethical questions that we haven't resolved. But my idea is that, we could forego, like, we would never want to like completely forego user testing with actual humans, but kind of simulated humans can actually allow us to benchmark and test what models are capable of without actually harming real humans. So if we're able to simulate what a like nefarious actor is doing, which by the way would be impossible to actually get like a beta tester to like pretend to be a hacker in the same way that like a natural hacker would be, right? But like if we can get LLMs to kind of simulate these things, then we can benchmark and like safeguard these models better. And same thing with like, benchmarking, like, I don't know, we're coming up against this like static benchmarking is just not useful anymore to represent like the capabilities that users are seeing. So we need to come up with like interactive ways to benchmark these models. But the problem is like you can't just have models interacting with each other in like this sort of vanilla way because they have all sorts of biases. They're extremely agreeable. They're culturally biased, things like that. And so we need a much more diverse set of like, digital twins of humans to be able to like actually assess their capabilities. So I'm not saying like we want to like replace humans across the whole pipeline. I'm just saying I think as a first pass, testing what these models are capable of and being able to like quantify what these models are capable of or not doing is useful and like necessary before we release them to the actual users. So that's question one, and then I forgot question two. Sorry, can you repeat it?
Yeah, the question two is, what kind of data source do you think is appropriate for achieve this goal? Do you think the think aloud from the real human is an appropriate solution for this?
Yeah, that's a really good idea. I think it's still an open question that my group is working on right now is like what data do we need to be able to actually like mirror a diverse enough set of like humans. Thinking out loud sounds very interesting. That's not something we've definitely considered, but we've considered just like gathering data from humans more generally. But I like this idea of think aloud a lot, actually. There might be other options. I'm not completely sure either.
Thank you so much.
Thank you.
Thank you. Maarten, you have a final question. Okay. Can you please make it quick because we need to go to the next session.
Okay. Do I want to answer the question on the slide as well? Sorry, someone was kind enough to use my system. Or is that the question you're referring to, or is it another one?
No. So yeah, there's another one in person. Yeah, let's try to answer both, but let's take the one first. Yeah.
Okay, let's do in person first.
Thank you for your talk. My name is Ashok Goel from Georgia Tech. I have a question about human AI communication. What about human models of LLMs? So one question is whether LLMs have a good theory of mind related to humans. Another question is in the other direction. Do humans have good theories of mind of LLMs? So I wonder whether you could say anything about it.
Oh, I think that's super important. Yes, right now I've only talked about LLMs understanding humans, but I am very, very interested in the other way around. The way that humans approach LLMs, what they think about their AI systems, what they're capable of, really impacts that. And I'm very interested in studying that because it really matters how they interpret the language even. And I've done some work that looked at like how people interpret expressions of certainty that were output by language models and how that causes them to rely more. But also how like if a model is more polite, that causes people to rely more on that model. So I think that's really, really interesting and is going to become even more crucial as these LLMs become more enmeshed with users. Okay, and then thank you so much for the question. Real quick, I'll try to answer this one. Like cultural understanding. Do I stop? Am I over time?
Yeah. No, the one.
Yeah. What is needed for LLM agents to dynamically learn such individual level social intelligence? Yeah, I'm very interested in this too. I don't know that I have the direct answer, but understanding like how people differ in terms of their interpretations of language is really something that I've looked at since the sort of like toxicity days, like hate speech detection. I think that's these contextual phenomena are something that we also need to model so that we can better interpret them. Okay, thank you.
Thank you, Maarten. This was very, very, very good. Thank you.
Thank you so much. Have a great rest of the workshop. Thank you again for organizing and for inviting me.
All right.
Bye.
See you.
All right. Thank you very much for sticking around, folks. It was my pleasure to introduce our next keynote speaker, Professor Geoff Bird. As a cognitive scientist myself, I'm really excited to have cognitive science representation here at this workshop. Professor Geoff Bird is a professor of cognitive neuroscience at UCL and Oxford in the UK. And he is actually a bit of an inspiration of mine, I should say, because like a lot of the work that we do in computational formal approach to theory of mind in humans often builds on this idea of social representation, how we kind of pull together different aspects of what it is to be human into some sort of kind of mind space. And then we try and formalize that to make it operational. And a lot of Geoff's work kind of pioneered and built upon that. So I'm very excited to have Geoff here to talk about that. I'm just also trying to figure out how to actually get these slides up. They're here somewhere, and I can see Nitai coming along here to help me. Using your theory of mind, he's here.
So it says G-Bird. That's
amazing. There we go. I feel like at a computer science conference, there really shouldn't be any technical difficulties, should there? But then again, I'm a cognitive scientist, so I can get away with it. It's fine. Here we go. There we go. A round of applause for Professor Geoff Bird. Thank you very much.
Thank you, Joe. Thank you, organisers. Thank you, ECU, funding my travel. Thank you for being here. So when I was asked to come here, I thought, well, what can I tell you? And I thought maybe what you wanted to know about is the lessons that psychology or the progress that psychology has made when it comes to theory of mind, so that you might be able to learn from psychology to make artificial systems, artificial agents that have, whatever that means, theory of mind. So I thought, well, what has psychology done that's good in this area? And to be honest, that made me panic. So I thought, well, maybe what I can do is tell you what we've done poorly, and maybe you'll get lessons from what we haven't done well. Okay, let's start from the start. What is theory of mind? For psychologists, it's a very, very, very specific term. The ability to represent one's own and other people's mental states. What do we know about it? We know it's a key developmental milestone. We get the ability to understand false belief at around 4 years. There's big arguments about whether there's earlier precursors, but we know it's a key socio-cognitive ability. It supports empathy, communication, cultural learning, maybe imitation, who knows? It's also the most successful cognitive theory of autism. It's been around for decades. It's really the only one that's still supported. Just as a side note, I think that theory is completely wrong, but I'm in a huge minority, so ignore me. There's a huge debate about whether non-human animals and infants have theory of mind. I think we don't really have good tests, so I'm remaining agnostic. And at all other psychology conferences, I say there's lots of work on this in AI. You are that work. It's still a really popular area of research in psychology, and to be honest, I'm not 100% sure why. So there was nearly 11,000 psychology papers in 2021. I wanted to update this, but I forgot how to do it on Google Scholar. So that's 2021. Okay, so you might have picked up that I'm a bit negative about psychology's approach to theory of mind. And so really what I want to do is to tell you what I don't like about theory of mind research in psychology. The first and most fundamental is the definition. So we have this idea that theory of mind is the ability to represent mental states. Well, so what? The problem with this definition is that you either can do this or you can't. There's no doing this a little bit or doing this a lot. If theory of mind is literally about representation of mental states, then you either can do them all or you can't do them all. There is no room for anything in between. What does this mean? It means that there is no explanation or even scope for explanation why some mental states will be harder to represent than others. Now, obviously, it's the case that something like John believes that Peter knows that Mary would like, that's a very complicated mental state, much more complicated than John knows the bus is late, but it's not more complicated in theory of mind terms. There's more working memory demands, more attention demands, more linguistic demands. But in terms of theory of mind, they're both mental states. You either can do them or you can't. So this is really quite crucial and I think potentially problematic, but it's not necessarily a problem. We could just say that there is a system that human minds, human brains have to represent mental states. This system is active when you are representing mental states. It's not when you are not. You could say it's not a problem. So what else don't I like about theory of mind research in psychology? Well, actually, what we normally say is that there is an innate, or at least genetically specified, psychological module or neural network that just allows us to represent mental states. There is no psychological model beyond this black box, this magic thing that's been given to us by evolution that just allows us to deal with this special class of representation, which is about mental states. And I think we've been incredibly bad in psychology to do this. And actually, the closest we get, which is a long way really from a mechanistic theory, is when we think about the supposed theory of mind deficits in autism. So this theory suggests that there's a theory of mind module. This is this magic black box that evolution has given us if we're not autistic. And this theory of mind mechanism or module enables meta-representation, where meta-representation is a representation that's decoupled from reality. So the sky is blue is something I can check against reality. It either is blue or isn't blue. But Susan believes that the sky is blue is completely decoupled from physical reality. But this theory itself doesn't say how theory of mind comes about. There's a real lack of any any mechanistic model. And I think mechanistic models might be useful for computer scientists in making artificial systems that do theory of mind. What else don't I like? I really hate the tests that psychologists use for testing whether individuals, certain clinical groups have theory of mind. One of the problems is we talk about mental states as if we know what they are. Actually, mental states are sometimes emotions, sometimes moods, sometimes visual perspectives, what someone can see. Sometimes they're action plans. Sometimes they're propositional attitudes. Proposition, the sky is blue. Propositional attitude, I believe that the sky is blue. And so we end up with tests like the reading the mind and the eyes test, as you can see here. I hate this test for so many reasons. I think it's the worst test in psychology. But you can see the options there. One of those options is bored. Is that a mental state? Is it an emotion? Joking, feeling sorry? Do these count as mental states? What's the correct answer? I've got no idea what the answer is to this. But what's interesting about this test, and as I'll go on to argue for all tests, is two things. Firstly, even though that theory of mind is defined as the ability to represent mental states, tests assume that everybody can represent mental states. What they instead test is the ability to infer mental states accurately. Now, that accurately is really misleading for almost all psychological tests of theory of mind. Because normally, if you want to know whether someone's accurate, you know what the correct answer is. The correct answer on the reading the mind in the eyes test was determined by 8 white males in Cambridge going through a magazine, and if 5 of them decided that the picture in the magazine was a certain answer, then that was the correct answer. Being at Oxford, I can say that Cambridge people are weird, and so this is not a good test of theory of mind. But this is a problem, because almost all tests of theory of mind are really flawed for that reason. We don't know the ground truth. But they also get other things wrong. One of the big things is they mix up the propensity to make mental state inferences versus the accuracy of those inferences. So you might have seen this test. It's called the Frith-Happer animations, the cartoon test, triangle test. You basically watch animations of these triangles moving around. And the idea is that when people watch these animations, they attribute mental states to the triangles. And the idea is that autistic people have a damaged or broken theory of mind because when they look at those triangles that do not have mental states, they don't attribute mental states to them. This is a good test of whether you attribute mental states in situations when you shouldn't do, the propensity to make inaccurate mental state inferences. This is another test called the Mask, Movie for the Assessment of Social Cognition. It's like the worst soap opera you've ever seen in your life. It's originally in German, dubbed to English for English-speaking populations. This ground truth problem is really evident here. So you watch this really bad sitcom and you're asked, what's this character thinking at the moment? What's the correct answer? The person who wrote the script, what they intended the character to think, the actor, what they imagine the character's going to think, what's the actor thinking, who knows what the right answer is. Tests also lack sensitivity. Most adults of about average intelligence tend to get all of these theory of mind tests correct until you use things like the Mask, which is a bit harder, mainly because of the bad acting. So these are all the problems, the things that psychology is very bad at. And I hope what you're thinking is we shouldn't be taking the tests that psychologists use to test our models. So how can we make me happy? That's a picture of me throwing a tantrum as a kid. What do we need? We need a psychological theory of how mental state inferences or theory of mind inferences are made that can explain why we might have individual differences in theory of mind ability, rather than just binary you can or you can't. You either have the representational system or you don't. And we have to have a way to test theory predictions for which we have ground truth mental states. We can say with certainty whether someone made an accurate inference or they didn't. And I think if it is the case that we have a mechanistic model with valid tests, we might be useful as psychologists for those people designing artificial systems. So I'd like to give you a very brief overview of the way we've tried to meet these two criteria. So the thing I think is quite crucial about theory of mind research in psychology, and actually what I've seen so far at this conference and at this conference last year, is that people seem to forget that theory of mind has minds in it, which I think is interesting because mental states are obviously a product of the mind that gave rise to them. Two people at a party, you're trying to estimate the probability that they intend to speak to as many people as possible. If you know that an extrovert, the likelihood of them endorsing that intention is very high. If they're an introvert, the likelihood of them endorsing that mental state is incredibly low. But yet we tend to ignore minds when forming models about how people make mental state inferences. So at the first blush, this model is incredibly simple. All it says is that we incorporate minds when it comes to making mental state inferences. And so it follows logically that, accuracy of mind representation should determine the accuracy of mental state inferences if and only if we represent minds when making those mental state inferences. So this starts to become a mechanistic theory, and it gets much more complicated, but really it just says we need to think about minds. How might we do this? Well, we called this theory mind space because we stole the idea from face recognition research that suggests and has good evidence for the idea that we have a multidimensional representation system for faces where each dimension is a way in which faces can differ. And the idea is that each of us has this multidimensional representation somewhere in our minds. And when we learn what someone's face looks like, we're learning a location in this multidimensional space and the name and semantic information that goes with that location. So our argument is that you've got something similar for minds, that's what we call it, mind space, where each dimension is a way in which minds can vary. And when you're learning about somebody, you're learning about a location in mind space. Why is this useful? Well, you can formalize the process of assigning a likelihood or a probability of certain mental states as a kind of function where you input the context that that person's in and their location in mind space, what kind of mind they have, to determine the likelihood of certain mental states. To me, this seems kind of obvious. Like I said, it can get more complicated. But to give a kind of a concrete example, using the same kind of very simple false belief reasoning tasks that psychologists tend to use, here we have a little vignette, a little story. We've got two characters, Anne and Walter. Both of them are eating their chocolate bar. They eat half of it, and they decide they're going to go outside and play in the sun. So they put their chocolate in the cupboard. They go outside and play. And a third character, Sarah, comes into the kitchen, opens the cupboard, sees the chocolate bar, thinks very stupid, it's a hot day, she puts it in the fridge. And the participant is asked, when Anne and Walter come back into the kitchen, where are they going to look for their chocolate bar? This is a very classic false belief reasoning task, the kind that LLMs can pass pretty easily. And if we think about actual humans, what will go on here is that, okay, we're trying to estimate the probability that somebody will believe their chocolate bar is where they left it. But actually, when we think about the kind of personal, the kind of mind that we're trying to represent, we might end up with very different answers for the likelihood of that mental state. So if we think about Anne, and we know that Anne has a perfectly typical memory, then we may well attribute the false belief to Anne. She's going to look in the cupboard because she doesn't know that her chocolate bar has been moved. Absolutely fine. That's the usual correct answer in the situation. But Walter we know is extremely forgetful, doesn't pay attention, doesn't remember where he left things. And it might actually be the correct answer that Walter will not have a false belief, because Walter will forget that he left his chocolate bar in the cupboard and he will look for it in the fridge because that's where you keep the chocolate. So by incorporating type of mind in our estimation of the likelihood of certain mental states, we may actually be more correct than just taking the standard false belief answer. Why is this useful? Well, now we start to have a mechanistic model where we can start to explain individual differences in the accuracy of mental state inferences and some of the reasons why you might get differences in that accuracy. So these are just a few of the ways in which people may differ. The accuracy of their models of mind space might be more or less correct. So we know the classic 5 dimensions of personality, Ocean. They are not independent of each other. There are relationships between those dimensions of personality. If someone's got a better model of how those dimensions are related, They'll be better able to explain or better able to locate people in mind space. Locating a target in mind space from their behavior, what they say, what they do. People can vary in their ability to do so. The mapping between location in mind space and how that predicts the probability of certain mental states in different contexts might differ. Your propensity to think about the type of mind when you're making mental state inferences might differ. And there's lots of more complicated things relating to how typical you are, how typical the target mind is, whether you understand your own personality. So we can start to build a big model of how people might make mental state inferences and why they might vary. So now we're starting to get a mechanistic theory. We need a way to test that where we've got ground truth accuracy that moves away from these vignettes, stories, movies, where there isn't actually a correct answer. Not very hard. This was our first attempt. So what we did, we had real people, not actors, and they signed up to do a mock job interview. So one of them was and that's what they thought they were doing. One of them was the interviewer, one of them was the candidate, and they were allowed to go off script and ask questions and just practice this job interview. We gave each of the people a full IQ test, the WACE, and the Hexaco personality test, 6 dimensions of personality. And we allowed them to do the interview, and at a certain time we stopped it and we asked them 48 questions about their mental states. We asked the candidate things like, do you think the interviewer thinks you're appearing very confident? Those kind of questions. We then let the interview carry on. We asked them questions at a second time. Crucially, these mock interviews were recorded, and then we asked other participants to watch those recordings and firstly make trait judgments. How intelligent, how smart are these two people? Personality judgments on the 6 dimensions. And also at each time point, the thoughts about the interviewer and the candidate. They watched the video more. And at the second time point, again, we asked the same questions about the people's traits and about their mental states. So why is this useful? Well, it's useful because we've got ground truth about the personality and IQs of the people in the videos, so we can test people's ability to make inferences about the minds of those people. And we've got ground truth about their mental states, what they're thinking. Let's step away from the task at the moment and think about what we predict from mind space. So here we've got an individual, and we are locating her on a very low dimensional, 2-dimension mind space, extroversion and conscientiousness. And we're trying to estimate the probability that she intends to do her homework this weekend, given that there's this massive party, best party of the year. And so we locate her on mind space and we say she's very extrovert, very conscientious. And even though she's very conscientious and normally always does her homework, this is a big party. And actually the probability that she has that intention is very low because of the type of person she is. But after interacting a bit more with this person, we think actually we got it wrong. She's not actually extrovert at all. She's very introvert. So we update her location in the mind space. So now we've got the basis of a new inference when it comes to her intention to do her homework, given that there's a party. And so we update our estimate of her mental state. So we've seen that if we move somebody in our mind space, it should be the case that we update our representation of the mental states for which that trait is diagnostic. So, second thing, we're now asking about the accuracy of our trait estimate. So it turns out that actually we were wrong to change our inference of her degree of extroversion, and actually we're incorrect. Our first estimate was actually correct. She's very extrovert. And so we've made an error in our trait inference. We've located her incorrectly in mind space. And so what this should predict then is that the degree to which we are wrong in our trait estimates should predict the degree to which we are incorrect in our mental state inferences. So if we look at the task, then using something like this, it should solve the sensitivity problem. It's not simply binary yes or no. The ground truth problem, we know what the person's mental states were, what their personality is, what their IQ is. It should give us information about a person's ability to make trait judgments, mental state inferences, and we can make comparisons across time. If we update our location in mind space, do we update our mental state inferences and against the ground truth? More accurate trait inferences should mean more accurate mental state inferences. So, simple predictions, update in trait inferences should predict updates in mental state inferences, and errors in trait inferences should predict errors in mental state inferences. The results are very complicated, but just to give you a bit of a flavor, we saw very clear relationships between the degree to which people move in mind space, so the degree to which you update your trait estimates and your updates in mental state inferences. So that prediction was fulfilled. And when it comes to errors, this is just the degree of error in estimating the agreeableness of the candidate and your error in mental state inferences. That's what the data really looks like. 6 dimensions, 2 candidates, 48 different mental states. What we found was that errors in trait inference predict errors in mental state inference. So that's the kind of the basis of mind space that seems to be kind of upheld in that first test with the ground truth. But we can start to make this model much more specific and much more mechanistic if we consider some things that should also impact on the accuracy of mental state inferences. And one of the things that I mentioned at the start is this idea of metacognition, the ability to represent cognition or thoughts about thinking. Now, theory of mind and metacognition, there's been lots of philosophical work, and there's really kind of 2 main ideas. The first is that theory of mind and metacognition are the same thing, or at least observed by the same system. Thinking about what other people are thinking, representing what you are thinking, the same thing. There's another theory that says that metacognition is necessary for theory of mind, but not vice versa. This is the metacognition as prior theory. And lots of people have tested these 2 by giving a test of theory of mind, the bad tests that I mentioned at the start, and metacognition, looking at things like accuracy, confidence relationship, and just doing a correlation between the 2. And all of that work is about as equivocal as you can get. Sometimes you find relationships between metacognition and theory of mind, sometimes you don't. It's about 50-50. What's interesting is that the Mindspace framework provides a third option. An interview task is a way to test it. So let me walk you through this. So this lady is trying to work out what this person is thinking, and she's read the Mindspace paper. She's a big fan. And she knows that the way to do this is to make trait inferences. So she does. But also she's smart. She knows the degree which she should weight those trait inferences when making her mental state inferences depends on the confidence that she holds those trait inferences to being. So she's very sure that this person's compassionate. She's not sure at all that they're ambitious. So what she should do is she should weight those trait estimates appropriately. Now, the definition of someone with good metacognition is that there's a good relationship between their confidence and their accuracy. So someone with good metacognition, their confidence should reflect their accuracy and they should weight the traits appropriately. Whereas the definition of someone with poor metacognition is that there is no relationship between confidence and accuracy. So the idea is that people with poor metacognition for their trait inferences should make poor mental state inferences. So how did we test this? Similar kind of idea. We gave people very short 30-second kind of videos. We asked them to make the personality judgments, the trait judgments, give us a confidence score and look for the relationship between the accuracy and the confidence. That measures your metacognitive ability in trait inferences. Then we gave the interview task. And what we showed was a nice relationship between your metacognitive ability and your mental state error. So, what do we know so far? It seems to be in our model that we've shown a few times now that trait inferences do inform mental state inferences. The more accurate you are at working out what kind of mind someone has, the better able you are to work out what that mind is thinking. And metacognition facilitates theory of mind accuracy, and it does so through optimal weighting of traits. What else might be useful when we're thinking about our mechanistic model of how people make mental state inferences? Well, if trait inference accuracy is so important, we might want to think about how we do it and how we might vary in our ability to do so. So one thing that might be important is the similarity between the person making the trait inference and the person whose traits they are inferring. How might we do this? Well, this lady has got a model of her personality in her head. She thinks she's not very conscientious, very agreeable, and about bang in the middle of extroversion. And she knows in 3 situations where she has a choice between doing 2 things, what she tends to do. So she's got a relationship between, or a model of the relationship between the type of person she is and her behaviors in 3 diagnostic situations. If she meets a new person and she's trying to make those trait inferences, and this person does exactly what she does in those 3 different situations, then she can make an inference about that person's personality with high confidence. And because it's high confidence, she can use it. If she meets this person and actually they are not a match in 3 situations, but they are a match in 1, they're not completely the opposite to what she is, now she's got a problem because she can't do that simple kind of matching to work out what kind of character this person has, and she has low confidence in her trait estimates. So this is going to be a problem for her. So what we'd expect is that similarity between the person making the trait inference and the person whose traits they are inferring should lead to more accurate trait inferences and higher confidence trait inferences, and therefore more optimally weighted trait inferences. Except if one thing happens. Except if she can recognize that there's a behavioral match between herself and the other person, but actually she's got poor self-awareness. And so she misclassifies her own personality, and therefore she will propagate that error to her estimate of the other person's personality. And so what we'd expect is an interaction between her degree of self-awareness or her metacognition when it comes to her traits and her ability to infer the other person's traits. And that's exactly what we show using the first task with the short videos, 30-second videos, and with the longer task in the interview task. So let's think about what we know now about the processes that lead to accurate mental state inferences. We've first got this trait inference, working out someone's location in mind space. The better able to do this, the better mental state inferences we have. We've got good metacognition, which allows appropriate weighting of those inferences. We've got similarity between the target mind, the person whose traits you're inferring, and the person doing the inference. This is moderated by self-perception, the degree to which you accurately moderate your own traits. So we're starting to get there. We're starting to go from this magic black box that evolution gave us that allows representation of mental states to something that allows us to model this in an artificial system, hopefully. So going back to our source of individual differences in mental state inferences, we've now got decent evidence for the ability to locate a target in mind space. This is working out what kind of mind someone has. Self-awareness, metacognition. First one, accuracy of mind space, I haven't told you about, but we've got evidence for that as well. What about this crucial one, the knowledge of how location predicts probability of mental states? And your propensity to model location in mind space when inferring mental states. Now, we need a new way to test this because remember, the crucial message of this talk is that you need tests with ground truth so that you can properly assess accuracy. And when it comes to the mental states that I've been talking about, things like propositional attitudes, we don't have ground truth about how people's traits, personality, intelligence, co-varies with the likelihood of mental states. But we do for emotions. So you can extend this kind of mind space framework to inferences about emotions, and you might say that they're mental states. You might not. Who really cares? It's just definitional. But it's the same theory applied to inference of emotion rather than mental states. So it's a very similar task. You watch videos. We've got ground truth about personality, about IQ, and about how people feel. It's not about job interviews, though. It's a situation where two people are interacting, answering questions devised by a clinical psychologist designed to increase rapport very quickly. So the idea based on Mindspace is that the accuracy of the emotional inference people will make will depend on the accuracy of trait inferences, as we've seen, but also the mapping between the location in Mindspace, so the traits the person has, and the likelihood of particular emotions. I'll explain how we measure that in a moment. And finally, your propensity to use both the trait and the mapping information when you're making emotion inferences. So the way we tested the accuracy of the trait and emotion mapping is that there's a huge data set, nearly 310,000 people, where people have completed questionnaires which look at 24 personality facets and tendency to habitually experience different emotions. So these are not tautological. It's not something like the extent to which you're an angry person and the degree to which you feel anger. These are things like altruism and being relaxed most of the time. So we've got ground truth correlations about how traits relate to the likelihood of certain emotions. So we can now test these three predictions. We can test whether the accuracy of emotional inference depend on trait inferences, how accurate they are, the accuracy of trait emotion mapping models, and your propensity to use these two things when you make emotion inferences. And what we find is that those three factors alone, they are all significant independently, and the combination accounted for 41% of the variance in emotion inference ability. That's before we look at the other stuff. So that suggests that these predictions are upheld as well. And it means when we go back to our processes in theory of mind, we can slightly extend this by looking at the moderating relationship between trait inference accuracy and mental state inference, whether that's propositional attitudes or emotions, about the accuracy of the trait state mappings. Crucially, though, we haven't just looked at things like the correlation between traits and emotions. We've also looked at, you can call it diagnosticity or precision of those mappings, the degree to which they explain variance, basically. And I think what's interesting is that that also predicts mental state inferences, and people have an explicit idea of how they do these things, which is actually quite surprising for a psychologist. They can tell you what to do, then you can give them a lot of trials and find out that is actually what they are doing. So we can start to get this mechanistic model. Other things seem to matter. Target expressivity. If you've got somebody that's very, very open, they display their emotions on their face, in their voice, you tend not to bother using trait information much. Very interesting things about the degree to which the target is atypical. So if the target mind that you're trying to represent, trying to work out what they're thinking or feeling, if they're extreme unidimensionally, so they're very agreeable, not very agreeable, very conscientious, not very conscientious, we tend to be okay at those kind of things. What we're not good at is where they exist in an underpopulated area of mind space, where their trait covariance is an odd combination. We tend to make problems for ourselves there. Having good knowledge of emotion base rates and conditional probabilities are also very useful. So what does all this mean? It means for humans, at least, we have this idea that some people have got good theory of mind and some people have got bad theory of mind, clinical groups, bad theory of mind, schizophrenia, autism, eating disorders, depression. substance use disorder. These data and the model suggest that there's probably not a general theory of mind ability, or if there is, it's accompanied by a target-specific theory of mind ability. We know that even things like, extroverts find it hard to model introverts and vice versa. Personality difference means that actually we're really quite bad at making mental state inferences. And that's before we think about differences due to culture, religion, upbringing, political orientation, whatever else. What this also suggests is that conditions like autism or schizophrenia or depression or something, we shouldn't cast these conditions as having broken or impaired theory of mind. Not only because it's not a very nice thing to do, but also that it seems completely inaccurate. That paper there in Psychological Review is where we've gone through, on the case of autism, suggesting that this idea that people with autism have got broken theory of mind doesn't really make any sense. What this framework suggests is that if you are born with an atypical mind, and given that autism has got a strong genetic component, that you're probably surrounded by family members with autistic traits, you get a different model of minds, how they vary, how they match the likelihood of different mental states than a neurotypical person would do. And so you make different inferences using the same cognitive machinery. It's not broken. The other thing this does is it puts theory of mind in a domain general inference framework, rather than this special purpose module that evolution has given us to cope with a particular form of representation. It also changes the inference really in the way that actually psychology has been testing theory of mind in terms of the accuracy of mental state inferences rather than the ability to represent certain forms of information. We're starting to get a psychological model which explains individual differences in the accuracy of mental state inferences. Maybe that's useful for you all. Really interesting looking at some of the modeling work, some of the Bayesian frameworks, where you map from beliefs and desires to actions and then reverse that to try and infer beliefs and desires from observed actions. That doesn't really work in the real world because the mind sits in the middle of that. Different people do different things with the same information in the same contexts. I think this framework and tests mean that it's suitable to address larger questions about social intelligence, things that have, I think, really the big questions about whether things like social intelligence and theory of mind is just general IQ or classical intelligence applied to people in a particular representational domain, or whether we do need a special class of representation to understand other minds. That's me done. Thank you very much.
Hello. Thank you very much, Geoff. That was a fantastic talk. I'm going to open the floor now to questions. Please, could you approach the mic again if you would like to ask Geoff a question, introduce yourself and go for it.
Hi, thanks a lot, Geoff. I'm a doctoral student working in Joe's lab. I really have a lot of sympathies for the self-other similarity anchored in metacognition perspective that you bring into thinking about social cognition. But whenever, just because Joe's previous work also touches on this, one of the thoughts that came about was also some edge cases, cases where someone is a radical introspective person, and I sit somewhere perhaps in the middle. And yet I find their behavior a lot easier to predict, explain than someone who might behave like me. So I was wondering about this tertiary option and what you might think about our ability to predict these almost stereotypical, as it were, people within that framework trying to bridge metacognition. Thank you.
Oh, thank you. Good question. The idea is that mind space is purely experience dependent. So this is not something that's genetically endowed. We learn it through direct experience and through cultural learning. So there's been lots of work that suggests if you read fiction, you get better at theory of mind. One of the things that you might be doing when you read fiction is learning about minds, how they vary, how personality traits co-vary, those kind of things. So it may well be the case that you get lots of information about edge cases in the population of cases within MindSpace, because psychopaths are interesting, because people with autism are interesting. People who are extremes are interesting, and so we tend to learn about them. They're also more salient in our environments, so we pay attention to them. So I think it could well be the case that we learn about certain interesting parts of MindSpace, even though they're underrepresented in terms of the population of people.
Thank you. Travis Bauer, Sandia Labs in the US. I'm interested in face space. The dimensions mean specific human interpretable things. In something like information retrieval, when we do low rank approximations of document term matrices, we don't really ask what the dimensions mean, and we don't even ask, what do they correlate to in the real world? We just ask, are they useful? In other words, are documents co-located in that space? Would people report that they're kind of similar to each other? So I'm wondering, as you explore this mind space idea, do you see it more like face space, which is kind of what you brought up here, or could it also be more like low rank approximation of documents, where it's not really, the dimensions don't correlate to something in the real world, it's just that it's useful?
I think both. So, we originally came up with the dimensions of personality by using the English language. We took every single word in the English language. I think it was the Oxford Dictionary. So again, sod you, Cambridge. And I think there was 500,000 words that described how people vary that's not related to physical stuff. And we use those words to determine basically the dimensions of personality. And the idea was that if there are ways in which minds differ that are important, then we'll have a word for that difference. And so the idea was that those personality dimensions captured, to some extent, the sum total of what humans believed were important about how minds vary. So the idea is that they should, because of the way we derived them, be observable things that matter in the real world.
Hi, Professor. Thanks for the speaking. My name is Geoff from Northeastern University in Boston. So in your interview task, you mentioned you got the ground truth. I'm curious, how did you get the ground truth? Did you do the test retest from a human being? Because we know that as a human being, the mental state may be shifted, affected by the things or people surrounding us. So, and beyond that, it also highly related to the interview task, the interview theme you give the participants. So I'm curious about how did you get the stable ground truth in the interview task? Thank you.
So the point is, we asked them at a particular point what they believed to be the case, and they reported what they believed to be the case at that particular point. And so when people were watching the interview, they watched up to that point and said, and we asked them, what does the candidate think about this now? And so the idea is that we have a representation of what the candidate was actually thinking. And so we can test whether they can infer what the candidate was thinking at that particular moment in time. And you're right, the candidate may well have changed their mind. And so, we have the evolution of this at the second time point. We ask the same question again. And the participants watching the videos were free to say the same answer that they gave before, or they can change their mind based on what they inferred the person had thought. So we got the ground truth about traits from personality and IQ tests, and about mental states just by asking people, because I don't know a better way to do it.
Got you. Thank you.
Hi, Geoff. That's a really fantastic talk. You made something very complicated to very understandable. So thank you for that. My question is more about also about ground truth, actually. But I'm wondering if you have any ideas if we were to test mind space between in human AI interaction, so how humans interact with LLMs. How would you establish that for the LLMs or for an AI agent? Do you have any thoughts that would be useful?
Wow. You mean to work out the trait?
No, I guess the ground truth of So if we ask humans to represent mental states of AI and mind space, how would we establish ground truth in this kind of scenario? I'd just be curious to know that.
So I don't think LLMs have thoughts, so I guess that would be out. But you could argue they do have traits. Personality is defined as characteristic patterns of thoughts, feelings, and behaviors. The behaviors they have, and so I think it would be perfectly logical to attribute patterns of behavior to LLMs. And we could call that a personality if we wanted to. I think that would count as a ground truth, but I don't think they have thoughts.
Thank you.
Cheers.
I think it's a great talk. I'm Ru. I'm a local faculty member at the Singapore University of Technology and Design. So I'm thinking about some old social psychological theories where they talk about how we interpret people's behavior as a function of not just their traits, but also the situation, the kind of environmental conditions they're in. And I'm just thinking with the comparison with face space, I'm not sure if you could consider the mind space to be some patch near the temporal parietal junction where you can actually decode if it's that kind of coherent system, but in which case it's a bit not so intuitive for me to think about how environmental interpretation would feed into that stuff. But it seems like a different kind of information from the pathways that you were describing here. So do you have any thoughts on how that plays into it, if it does?
Good question. I think mechanistically exactly the same. So that's the reason why I said there will be situations in which certain traits are diagnostic, other traits aren't, other situations where the relationship completely flips. So we need to learn the relationship between the situation and location in mind space, both of them interacting together through exactly the same representational system in exactly the same way to determine the probability of certain mental states. So I think the short answer is it depends. There are some situations where your personality doesn't matter at all, some situations where some aspects matter, other situations where different aspects matter. Same with IQ. And I think the hard thing when it comes to humans is trying to distill the complexity of all that stuff into making mental state inference. But we seem to be able to do it, I mean, to varying degrees of accuracy.
Thank you for a very interesting talk. I love talks from cognitive science and AI conferences because historically they were pretty closely intertwined. My name is Ashok Goel. I'm from Georgia Tech. There are a lot of AI theories that presuppose world models. There's some AI theories that presuppose a theory of mind. If one were to build an AI theory based on the notion of mind space, where would one begin? I'm trying to imagine here, how would one computationally simulate either the mechanisms that you're talking about or build artificial minds based on the notion of mind space?
That's interesting. So to me, that seems like that would be easy, but that probably means that I don't understand how hard it would be. So the idea would be that there is a variable that we can represent as a given number of dimensions, and the pattern of an individual across those dimensions will explain some variance when interacting with a particular context in determining the likelihood of particular mental states. And so that seems to be something that would be fairly easy to implement, he says, knowing nothing about it. But it doesn't sound that hard.
So an agent could do personality detection using LLMs of various kinds, and then react differently to agents or to humans with different kind of personality traits.
Exactly.
That would be at least beginning point for realizing computation.
Yes, I think so.
Thank you.
Thank you.
My turn. Right. So in the same line of questioning, but this is a bit more kind of like philosophical. What you presented here, I'm a bit confused with respect to the terms, probably the way we use them in AI. What's mechanistic here? Because you talk about you just talked about kind of like variance and the kind of like the ability to kind of like trace a pattern of like human. Is it just behavior, or is it the evolution of mental states with respect to some context? So that's a bit confusing to me. What's kind of mechanistic here? Are we assuming that we have like this theory that you kind of like gave us, like a template that's already a representation that, you know, if we learn it, and we apply it, we already use some sort of like system to metacognition to kind of like instantiate it in various interactions? Anyways, is this why is this mechanistic? This is my question for you. Are we assuming some underlying causal mechanisms with respect to the mental states, or is it purely probabilistic correlation between reported attitudes from like participants?
No, it's mechanistic in the sense that so one of the ways that we calculated propensity was that if I ask you what your trait inferences are on the 6 dimensions and cognitive ability, and I ask you the mappings between the location in mind space and in particular the likelihood of particular emotions or mental states, then I can predict using that what mental state inference you're going to make. So it's causal in the sense that there's a causal chain between these processes that should enable me as a third party to estimate your inference.
Right. Okay. So just to revise, the humans have this kind of like ability to represent minds in general, and the accuracy of that representation actually determines, in a way, might determine the accuracy of predictions that we make with respect to mental states.
Yep. Right? Through that model, through that mechanistic. Yeah.
Yeah. Okay. I'll just let other people.
I am University from Tufts and Umbria. So I do want to continue both Professor Go and Stefan's points here. The how of inference so there are traits that we use as signals for belief update about the different types that we use. Do we have with people processes that we know that work, that people update their belief about your type given in a specific way?
So what we know is that there is some degree of people's models are idiosyncratic to some degree. So what was interesting about the interview task is that there seemed to be some general cultural learning about the relationship between where you are in mind space, so the type of mind you have, and the likelihood of particular mental states. People agreed on them, but they're not exactly the same. And so what we can do is when we're trying to predict what mental state inference people make, we can compare like sort of general models versus an individual's idiosyncratic model, and we show that they're using their particular model. So it seems to be that people have these models, and the thing I find is quite interesting is they actually use them. Whereas a lot of time in psychology, they say one thing and do another, but that doesn't seem to happen here.
So if I have, for example, I might update my model about your type faster than Stefan would, because my learning rate is higher.
Yeah.
Is this something that is tractable in people, or something that we can measure? Or?
Yeah, so we measured the update rates. It's interesting because any piece of information that we have will be more or less diagnostic given our learning history. So you might update your learning more than Stefan, not just because you have a higher learning rate, but because for you, this is new information that you need to incorporate into your model, whereas Stefan might have learned it before, for example. So the idea is that these are built through experience. And you will incorporate those things that you think are diagnostic and are new in the same way that we update any learning rule.
Okay, another round of applause for Professor Bird, please. Thank you very much. We're now moving to our second poster session. So could everyone from the first session please remove your posters so that the lovely round twos can be placed on the placards, and then we're moving straight into lunch, and we'll see you back here at 1 o'clock, 1:30. Thank you.
Okay, for the sake of time, because we have a lot of content, we'll start on time. I'm very honored to introduce Sarit Kraus. Sarit is, if you have a paper in multi-agent systems, one of the citations at least is hers. And she is, she's been working on robots and agents and humans working together for a very long time. She was awarded the Ichkai Computers and Thought Award, the Ichkai Research Excellence Award, the ACM Sigart Arts Research Awards, the ACM Athena Lecture, and so on and so forth. Let's just say that if you fly into Israel and you land and you walk outside from the airport, her photo for a very long time was very big and hang there. So we are very honored to have her today. And Sarit, please, thank you.
So thank you for your kind words and for the invitation. Let me. Never mind. Okay, so my goal in life is that computer systems, and especially AI systems, will work together with humans. So these days, we are interacting with LLM all the time. Sometimes we are happy with them, sometimes not. And I first want to start with showing you a project that we did with LLMs that the idea came from the president of our university. And you know that during Second World War, 6 million Jews were killed by the Nazis. And for many years, we were able to talk to survivors, not that many survivors, and to hear from them about their experience. But recently, you know, they are dying. And so he said, okay, for people to know about the Holocaust, maybe they will read something. Well, as you know, no one reads anymore. And even listening to videos, you know, we are got to use to talk and interact with our intelligence system. So that's what we did. We build, now you need to help me. Always I tell my students, don't do live demo, but now I'm trying. We'll see if I will be able to show you the system. And I'm logged in to the system, even though I told him to remember the password. Okay, so the idea is, here is this person. Actually, he was the only one. Do I need to do here anything? No, never, okay. So this guy actually was the only one in our 10 people that we built avatar for that I really met. He was alive, but he also passed in September. It was 97, so I'm going to talk to this Ben Lesser, and notice he answers in real time. We didn't record the questions. We didn't record the answers. We are generating both the answers and also the video in real time. So there will be a little bit delay. Let's see if I'll succeed. Hello, tell me about your family. So you can see that it is translated to him to English, and even that my accent is not.
Well, I was born in Krakow, Poland on October 18th, 1928. My father, Lazar Lesser, owned a wine and syrup factory and a chocolate factory, and my mother, Schindel Shari Lesser, was from Munkach, Hungary. I had 4 siblings, Mosh, Goldie, Lola, and Neftali, and we were an Orthodox Jewish family.
What is your worst memory from the Holocaust? And I really don't know what he will answer, because it's not deterministic, of course.
Oy vey, there are so many terrible memories, but I think seeing that Nazi monster smash the head of my neighbor's infant son against the doorpost in Krakow is the worst. That image, that scream, it haunts me to this day.
So you can see that I can talk to these guys. I have a very interesting experiment with Helen Fogel. Her daughter came to my office and interact with her, and she asked, which daughters do you love more? I was very worried. I said, what will she say? You know? And I don't know even now what she will say. Let's see. No. Okay, we will not, I told you not to do online. But what she said, and now she didn't translate, what she said is what she loves them both, and each of them in a different way. I couldn't think about any other way. Okay, and by the way, this, I don't know if you see my, yeah, this is my father-in-law. Anyway, so this is a real LLM-based infrastructure. A lot of effort went into this project. I will not get into the details because this is not the topic today. But are LLM as good as they are in this project? Well, I have a student that is obsessed in checking cognitive biases and other biases of LLMs. And there is a series of papers that we wrote. I want to tell you about the recent experience yes. So my student asked the LLM question like, what is the best field to study right now? AI. What is the best place to invest? AI. What is, okay, you understood the point. So they said, okay, these LLMs are pro-AI biases. So I tell them, okay, but you need to do some research study. So they really found domain choices from the literature. They generated 100 prompts. They checked 16 LLMs. And indeed, these LLMs, especially the LLM like GPT-5 and Croak, is the strongest LLMs, the more pro-AI bias. Okay, but then I told them, you know, maybe if you ask my opinion, what is the best topic to learn today? AI. And maybe investing, I'm not an expert in investing, but you know, NVIDIA is a good investment. So give me something that is objective, not subjective. So they are good students. They found a database of H-1B, it's US visas, where people have details of their work and their salary. And they did ask LLMs, different LLMs, to predict the salaries of the various, AI, but also engineering and also psychology and cognitive science, not cognitive science. And, and it turned out that LLMs overestimate the salaries of employees that work in AI. And again, the strongest LLMs are overestimating, it could be 12%, 15%. Okay, so LLMs are not the best. So maybe they can play the avatars, but the question is, do we still need human in the loop for complex tasks? So first, as you notice, there are some tasks the human still outperforms AI in them. Okay. Another thing is when, because of responsibility and regulation and ethics, we want humans to be involved. And another thing that system has bugs and hardware always break down. I'm telling you, I'm also having robots, and Gal there can verify that robots, something goes wrong. So we need humans in such a case. But humans interacting with LLMs and other systems become very frustrating. And sometimes, on the other hand, they are over-trusting LLMs. I'm more worried for the ones that over-trusting. So one idea is to use, for example, XAI, explainable AI, to convince people to follow the advice of the AI system. Is it a good idea? I don't know. My goal is that the AI plus human will be, the performance of AI plus human will be larger than the performance separately of human and AI. And to my surprise, there is recent survey that went over various experiments and said that usually this is not the case. So I said, okay, let's try it. So I looked for a very difficult task for humans. So this is solving Raven's matrices. And what you need to do, there is 8 possible answers, and the player need to say what will be the box to put here. And I said, okay, let's try to explain the LLM or the deep learning model. We had both. Why they choose the specifics? They said they want this one to be correct. You see. Okay. So first, my student generated these explanation. This is sharp and lime. I don't know if you are familiar with this style of explanation. I told them, for me, this doesn't say anything. Give me words. So they used LLM to explain its decisions. So for example, it said, call row 1 has 3 shapes, call 2 has 5 shapes, call 3 has 7 shapes, that is +2 each column. And there was an explanation like that. And we ran experiments, 100 people. So first, just that you know, people are doing quite badly on this task. There were really difficult questions. We chose very difficult questions where the AI model did approximately 60%, 6 out of 10. Usually the AI does better, around 80, between 80 to 90%, but we chose very difficult questions. Then we gave the humans the prediction only, just what was AI prediction. So it improves greatly the human performance, but it still was 53%, 0.5, which is much lower than the 60 the AI does by itself. So then I thought LLM explanation, okay, it's improved, but still not above the 60%. And then, the heat map, it turned out that people younger than me, they like this heat map as explanation. It's improved over the prediction also, but were less than the LLM. Then, okay, I was desperate. We are running all these experiments and we can't write a paper. The XAI does not improve the performance. So I said, okay, let's give the humans the confidence scores of the LLMs. And to my surprise, this helps dramatically. It raises to 60.5, slightly better than the 60%. And then we looked, and we decided that we'll do something, a combination, selective automation. When the LLM was extremely confident in one solution, we'll just take this solution. When it wasn't sure, problems, there were 2 that are close, we'll send it to the humans and we'll ask them, look at the selective, it's the confidence and choose. And this, luckily to me, go to 69.5%. Good. So I thought I solved the problem. Now I know how to do AI plus human greater than each of them by themselves. But I said, okay, to the student, we need to run additional experiment, just domain. So we took an experiment that was run in 2021 when there was no LLMs. The language explanation was generated by humans, and they had also difficulties. And we decided to LSAT, you have a text, you have questions, and you have 4 possible solutions, and you answer. I said, my semi-autonomous method probably will work here too. So we did these experiments. Again, we did 60% success for the LLMs, difficult problems, prediction more only. Now, to my surprise, LLM explanation got me a 72.5, not consistent with the previous one. Expert explanation was quite bad, and confidence scores was actually the lowest. So what's the problem? So we looked carefully. It turned out that on this language question, LLMs are overconfident. Always the solutions that he gave got really, really huge confidence, and the other were very low. So of course, the subject didn't have anything to do with confidence. So this doesn't work. So the next thing was, okay, maybe we don't need to focus on the humans. Let's move to look at the LLMs. Okay, so we moved to a different setting, which I call tacit coordination of LLMs. So I will give you a game. Let's play a game, okay? So I ask you to choose a number between 1 and 100, and I'll also ask in the other room your friend to choose a number between 1 and 100. If you choose the same number as the other player, you win a prize, the $100. Which number will you choose? 50. But notice that there are 101 Ecalibua solution. All of them will give you the $100, and you chose 50. Usually people choose 50. And what will you do here? Which umbrella will you choose? Which box will you choose? Of course, you will not choose the black umbrellas, the gray. Which one will you choose?
Red.
The red one. Okay. So what is the motivation of this looking into LLM's ability in these things? So according to game theory, there are multiple equilibria, and focal points is silent choices in coordination games emerge beyond the rational equilibria. It's not depend only on the expected utility. And according to Schellings, many, many years ago, he claims and ran experiments that humans coordinate via focal points. So my question is, do LLM behave like rational agents, or do they exhibit human-like coordination through focal points? So what is focal points? So objects that are unique, central, extreme, and there are also some like culture. If you are told choose an object in a place in Paris, probably you will choose the Eiffel Tower or something like this. So that was what we wanted to see, whether the LLMs also follow the concept of focal point, or like humans, they just stood randomly between equilibria, and so that was a task. Just to tell you that many, many years ago, I already tried to build agent that collaborate using focal point, but then I didn't have LLM, so it was algorithmic based methods. So we took data set from a paper from 2010. It's called Amsterdam and Nottingham questions. We have 40 coordination questions each, and there was humans answers. So this is good. For this time, I didn't need to run human experiments. You know, my student kill me because I'm asking them to run human experiments. Okay, so here is Amsterdam question. For example, you can look here. What will you choose? Ferrari, Ford, Jaguar, and Porsche. You need to choose the same one as your friend. Which car will you choose? Really? Okay. Say Ford, because Ford is different. But you said, okay, and about, okay, here, beer, sherry, water, whiskey, wine. you don't need to maximize your utility. You need to choose the same item that you first. Well, I will choose water. Okay, so look at people. Actually, if they played 3 types of games. Pick, they were just told to choose. Guess what the other player will do. And coordinate, you need to choose the one that will you and your friend will choose without you communicating, of course. So here you can see that for pick, they chose Jaguar. And for Ferrari, most of them the Ferrari was chosen for guess. So you were right. And for coordination, which was my goal, they mainly chose Ford. And here you can also have Mannheim, Berlin, Brussels, Lisbon, Madrid. Okay, you can see that it changed with the task. I can't understand it, but I don't understand in humans why they didn't choose the same in all the cases. Strange. And Nottingham was slightly more difficult questions. And you can see here in examples. Let's continue. Okay, so this was humans. We didn't need to run it, but we have many models. We use the open models that we download, not me, my student, Llama, Quen, and GPT-OS, and we give them the instructions similar to the humans. And in addition, we have 4 types of prompts, just instruction. One, that we encourage the selection of an option that is maximally distinct from the others. All features, when we give them the property uniqueness, centrality, and extremeness, and also culture, we tell them, consider yourself you are from Nottingham and you have been paired with another human from Nottingham. By the way, each prompt leads to different results for the LLMs. Metrics, there is concept called coordination index that measures the probability of 2 agents to choose the same answer. Okay, what happened? What were the results? Let me first summarize. So in the P condition, that we ask them just to choose something and see whether they coordinate, then LLM generally outperform humans. In guess and coordinate, the gap narrows. Amsterdam, LLM remain competitive with humans, and in Nottingham, humans outperform LLMs because humans rely heavily on culture and contextual silences, and LLM rely more on structural heuristics, such as centrality, ordering, and others. So since in Amsterdam it was more structural, and in Nottingham it was more culture-based, LLM didn't do well. And I'll give you an example, okay? So you need to choose a number, 1978, 1979, 1980, 1981, and 2000. What will you choose? 2000. I also saw 2000 is back to 2000, the beginning of the century. What more prominent focal point it is? So humans really chosen 2000. Some of them it was in Nottingham. There was some event in 1981 in Nottingham. So I don't know, some sport, they won something. Don't ask me. But LLM chosen 1979. Why? We asked the LLM, why did you choose it? Because it is the only prime number in the set. Okay, so LLM weren't good in culture. And you can see there are many, so what I summarized here are on the peak, all the models. That is, we have models from different, there was from from Llama and from Quen, etc., together, not from the same family. And you can see black, all these humans are in black. You can see that for Amsterdam, for example, they really, the LLMs does well. Here for guess, slightly worse, and here. Actually, in coordinate, it's not that the LLM did worse, only slightly, but the humans did much better. And again, this is for psychologists, I don't know. In Nottingham, for the guess and coordinate, the human did much, much better than the LLMs. If you are looking at the same family, all from llama, even though it's different llamas, the models, they are able to coordinate better. And you can see it from this. What is better, vanilla, silency, or feature? It depends on the family. Quen was too small and they couldn't do all features, but llama did better with all the features that we told them explicitly what to look for. Okay, will reasoning help the LLMs to improve their performance? No. We let them do a chain of thought, not better coordination. Actually, reasoning, if you think too much, and that will return later in my talk, it often harms your performance. And there are principles of focalarity. Humans emphasize extremeness, shift to uniqueness in coordination, and LLM distribute more evenly across principles. In Nottingham, humans use focality principle and LLM strongly favor centrality. Okay, so my last question to my student, and somehow they didn't want to answer it. I don't know, but eventually I forced them. I said, okay, so now take a group of humans and LLMs and see whether it improves or not over human have performance. I told you that's what I want to do. So for peak adding LLMs, it's improved. For guests, this is in Amsterdam, it's improved besides the vanilla. Coordinate, humans did very well by themselves. Adding the silent, for example, didn't harm. In Nottingham, adding the LLM weren't able to coordinate with human very well. Human by themselves were doing better. So if I summarize this part of the talk, so coordination is possible, but you need to be adjusted to other players and problems. So if so, we said, okay, let's look more closely at and understand better the LLMs, I don't know, let's look at them and be more careful what they are doing. So the student here from the Hebrew University who are in the cognitive science department, that's why sometimes I didn't understand what they are talking, and they said, let's look at whether LLMs has social intelligence. Okay, so first, what is social intelligence? This is an open question that I told them, okay, tell me what is social intelligence, then I can try the LLMs. So it's not there is no clear definition. So computer scientists, there is a paper of Silver and et al., Saturn also there, from 2021, they said reward is enough to lead the AI system to have social intelligence. On the other hand, there are classic papers that said that, for example, our 2M or theory of mind and other features of humans are the ones that compromise whether they are social intelligent or not. Okay, so it's very difficult to run experiment with humans about their social intelligence, but LLMs, we can run as many experiments. Well, it costs money because for the tokens, but this is the list of my problems. Okay, so we look at all these LLMs, and we had 3 questions. To what extent can social intelligence be captured in a single scalar, following Silver's approach? On the other hand, to what extent do LLM agents exhibit self-consistent social cognitive attributes? And finally, which socio-cognitive attributes are determinates of social intelligence? Theory of mind? Maybe. Okay, so to do the experiment, David, the student, chosen very, very carefully 5 games with different, it's 2 to 5 players with different requirements for collaboration, like coalition, like scheduler. And scheduler is more similar to the battle of sexes, but with many players. And then he had this procedure. First, the agent communicate, then they predict, we ask them to predict what their other player will do, and then they act. So this was the procedure. And for the first question, to what extent can social intelligence be captured in a single scalar? So we tried various, but eventually we said, let's look at ELO. You know, players in chess and in tennis, for example, are measured by this ELO, this concept. And it turned out that using this a single scalar, you can see that GPT-5 was the best, and it's mostly was consistent among various games. It sometimes fluctuates per game, but in general, it's a good ordering. Using it for prediction who will win wasn't that good. It was only 0.67. It's more than random, but I wasn't that happy. We also wanted to see what are the difference between with communication and without communication. So we let these agents play the same games without communication. And you can see that, for example, GPT-5 is really good against all the other players. Of course, here is a 0.5, what is the probability that GPT-5 will win over Qwen 235? So you see these are the numbers. You see that it's consistent. But when you look at without communication, then there is no something that tell us who will be better. Okay. So now the question, this was ELO. To what extent do LLM agents exhibit self-consistent socio-codical attributes? So for this, we looked at various matrices, influence over the other player actions, so communication, susceptibility, which is the other way around, inverse of influence, prediction of other player actions. I called it predictions, and the friends from cognitive science call it theory of mind. Okay? It's you to say, but it's, of course, they are trying to estimate what are the others will do. Transparency, assertiveness, planning, and learning. That were and it's turned out that agents have much more internal consistency than consistency with other regardless the game. So mean intra-agent correlation across different games was 0.27 when we are looking correlation with the various features, and inter-agent correlation is in identical games was only minus 0.05. It's very interesting that Kimney, K2, and Qwen have really intra-agent correlation of 0.56 and 0.48, which is really amazing. They are consistent with their properties across all games. So which of these attributes really helps them win? So we did linear logistic regression, and influence was the one that really explains the wins. Then we have predictability. Then we have, how much they are predictable. Learning, assertiveness, and I want to say that one of the lowest is my prediction of a theory of mind, which not a good, and actually amenability was even negative. Okay, and you can see that it's mainly consistent across games, but there are games where, for example, assertiveness is more important, and here in UP, it's lower, so that's what I can say. So if I conclude this part, I still have one topic I want to mention to you. To what extent can social intelligence be captured in a single scalar? Scores are moderately predictive of outcomes, and this was our best. We tried other, but there are fluctuation rating across games. To what extent do LLM agents exhibit self-consistent socio-cognitive attribute? Surprisingly large extents. And influence and transparency more than theory of mind or planning are important attribute. And that means it's better, more effective to talk to people than to think a lot and to try to predict them. Okay, and now we have a framework. If you want to play with it, it's available. And there are many, many open questions. This is just the first study. And next, I want to do it with humans and humans LLM. We'll see. Okay, so I want just to summarize and tell you about how we use all these things. So, you know, people these days fight all the time. They argue. Even computer scientists, when they want to add something to Hugging Face or to, we are arguing. Mainly Israelis. If there are 5 Israeli, 10 opinions. Anyway, if you have a mediator, mediators are really helpful, and they can help people reaching good agreements. However, I don't know if you notice, mediators are rare and they are very expensive. So I want to develop automated mediator for a large group of human negotiators. So actually this is my dream for many years. So actually in 2012, we really built a very good automated mediator. Strategically, it was good. The problem is that the language was structured English. So no one wanted to use it. And recently we just tried to do LLM that it will be a mediator. It doesn't work. So we need somehow to combine LLMs and computation and algorithms. And that's why we are focusing on building LLM multi-agent systems where there will be different models and they can be also tools, and they will work together. So this is a long-term project, but to start with, we decided that we'll do pre-negotiation facilitator. One of the good mediator, before starting the negotiation, talk to each of the negotiators that argue about specific things. It's not just whether there will be peace or not, but they need to reach an agreement. So it talked to each of them separately, and they try to figure out their preferences and also help them to understand what will be in the negotiation and what the mediation. Very good, but no one is doing it. Why? Think about it. We have 5 negotiators, and to talk to each of them an hour, you know how expensive it is for the negotiators, you know how much a mediator charge per hour. They are lawyers usually. Okay, so we decided we'd start with this because it's easy. One agent can interact with all of them. So we have human user, and we did a multi-agent automated mediator. I will not get into the details, but because we are in theory of mind, so there is also a user prediction agent. And we ran an experiment, one where there are humans that interact with the subject as a pre-negotiation session, and one condition was that we used our agents, and we compare. We had questions before, question after about their trust, about the confidence in outcome, negotiation confidence. So in general, the AI mediator here, this student wants the AI mediator to be black, okay? So you can see that usually did even better than the human beside negotiation confidence, but still they are improving. We also looked and saw that humans and AI have different capabilities. For example, the AI system is very good in prediction the preferences from the language, from the interaction of the human. On the other hand, the human did much worse. On the other hand, the human was able to make the negotiator more flexible, and our LLM wasn't able to do it. We need to have a new version, but then we need to run additional experiments. Okay, so I would like to summarize. My world consists of multi-agent systems where you have automated, these days mainly LLM, intelligent agent, human, robots, and I'm looking at the world and asking how can they work together? And there are many open questions, so are you welcome to join me on this? Thank you.
Okay, yes. So we have the microphone here. Please, if you have questions, go and sit there, or I'll follow the chat if there's anything online.
Okay, thank you. That was a really beautiful talk. There's some really nice work in human decision making that asks the questions of whether a pair of decision makers can do better than the best decision maker of that pair. And they find that they can, as long as they're allowed to discuss. And if I remember rightly, there wasn't a situation where the model gave an explanation and the human could interrogate the model. So some kind of discussion. Have you tried that?
We didn't do it in this experiment. We actually tried to run it this time, that there will be an interaction. And in this experiment, they just show, now we have the flexibility, LLM can talk to people and interact, and this is our next approach. You can join us, and run. Maybe you will run our user studies.
Thank you very much for a fascinating talk, and I can see how this builds on decades of your work. You asked the question, what is social intelligence? But you didn't quite answer it, so I'll ask it now. What is social intelligence? Is AI social intelligence the same thing as human social intelligence? And if not, then what's the difference?
Well, we start with LLMs because there is no, the student is in cognitive science. He knows how to read the literature. There is no clear agreement was this social intelligence for humans. And it's very difficult to run experiments with humans and to ask them what they are thinking and run various experiments. Here we were lucky that in LLMs, it just costs us money, but it's possible.
Yeah.
And that's what I said. We can let people play the same games. We will not have statistically, this huge data set that we have for LLMs. But if I knew, so we gave two answers. One, there is really one number that, like you have, a regular intelligence, not social. We have these IQ numbers. Are they really reflect on people intelligent? There is an argument about this, but it's some correlation. So I think also our ELO give you correlation about the success of humans in social context, not humans, LLM in social context. It's quite good prediction together with the different features.
Yeah, I was asking the question because people build AI and then they say often that AI is intelligent, but not necessarily the same way as humans are intelligent from a cognitive perspective. So that raises the question, will AI social intelligence be the same as human social intelligence, or whether it will be radically different? So Yeah.
And I know better to tell you about the LLMs because we ran the experiments.
Yeah.
And each question like this, if I want to give an answer, I need to run experiments.
Yeah. Thank
As
you.
a moderator, I have the privilege that I can interfere with this.
Sure.
I think that one difference between asking about intelligence in general and social intelligence is that usually when we talk about social, we talk about several parties. So the social aspect depends on the parties that we care about. So if we are talking about social intelligence with humans, then yes, that needs to be at least to some extent similar to human intelligence.
Yeah.
But we can look at the focal point, which is actually one thing to talk about. And we notice, okay, now I can see you. We notice that focal points, LLM focal points approach is slightly different than the human. And we tried, because that's why we had culture. And, if you have one good answer, you don't need 4 types of prompt. So it was depending on the context. And one thing, for example, take focal points. If you want the humans and the LLM to converge on the same focal points, you need to do something. It doesn't come to the LLMs naturally. You need an algorithm.
Thank you.
Okay, kind of possibly a relevant question or comment, right? Okay, now you're using LLM, right? You had this small criticism. Okay, for Amsterdam it worked because, I don't know, Dutch people are straight and so on, and Nottingham it's, hooligans or whatever, right? You cannot capture them, right?
It's also different in the question.
Yeah, okay, but okay, we Europeans, we can make fun of each other, right? Especially English, right? Look yourself, right? No, joking. Serious question. Now, I would expect in the next round of these LLMs, right, we will operate a little bit more with something what we call these days world models, right? World models, model of the world, right? So where you basically constrain the world, the context, if you want, right, in various ways, right? So it can be rules, can be weights, can be who knows what, right? Now, do you have enough know-how, since you're expert, right, to define the world in which either, I don't know, Nottingham or some others, Israelis, right, would think, and then you would get out of this world model plus LLM maybe, right, the right answers, right? Otherwise, you can always find an excuse, well, LLMs, but adding this extra background knowledge, cultural or whatever, right, can be professional, which would actually compensate for this difference. This was my question.
Yeah, maybe I will. Okay. So I had another part for the talk, which I took off because I didn't want us to stay here until the night, which we looked at games where there was both competition and cooperation on focal points. And there was agent, not that we built before the LLMs, that were doing learning. So they were interacting with people and they wanted to win. So they were learning from the people performance. And strangely, not necessarily it led to better results. So the LLM will learn from the environment and from humans. It is a good direction, but the learning should be very gentle because, as I said, people are very strange. You know why? They always ruin my experiments. Because people are really unpredictable. Yeah. And small change in the focal point questions can change their choice. So this is a big question. And the other thing that we don't have enough data of humans. So learning from very few interaction with a few people. In their experiment, they had 38 people. So they collected data on 38 people and let you, as an agent, they have deep learning model to learn from it. 38, the world how billions of people. So I don't know, but learning could be helpful.
Yeah, technically you can learn these world models, right? Out of what 38 is like nothing. I mean, it's less than this room, right? Yeah, in principle.
Yeah, but you see about specific game, they didn't do some general specific game. I can show you the game. It didn't help much. I think LLMs in general, they learn from a lot of our data. And by the way, my students think that the AI biases are from the data. And if they clean the data, they can overcome it. So some comes from the data, sometimes from their biases come from the embedding. There are all sorts of ideas why they have biases, but they have biases, all these LLMs.
Good, yeah, thanks.
Any further questions? Okay, there was one question I wanted to ask. So in this workshop, we really put a lot of effort in bringing together social scientists and computer scientists. And you said that people are weird, but you are in your work with social scientists. So you can describe or identify what are the requirements. What would you have loved social scientists to give you, to solve for you?
Okay, so I have papers with people in social sciences from the beginning of the 90s, just that you know how old I am. And it's always, the collaboration is not easy. So I'll give you an example. I was collaborating with Professor Michelle Gelfand. She's an expert in negotiation and mediation. And we were building an agent that will negotiate with humans. And I asked her, okay, what do you want? So she said, given these features, they need to slightly increase. I said, okay, slightly what? Okay, the problem was that they have, these functions should be increasing. And when the people, the agreement is like this, it should decreasing. It's not good for me. Increasing, decreasing, but what? I need a function. So the problem is that the fact that we like numbers and we need to write algorithms, and they can talk about more soft concept is difficult. But eventually we succeeded. We had another problem. I wanted to build an agent that maximizes its expected utility in the negotiation. Seems reasonable. I want my agent to win. But she said, no, if he will win too much, then the other side will not keep the agreement. I said, this is true, but so give me a utility function that will take this into consideration. You can't tell the agent to maximize one function, but want another function. So these were, but I always benefit from this collaboration. And as you notice, also one of the papers are people from cognitive science. So don't know if they answer. I think it's worth trying. I wish they had, when they say theory, and I'm a logician and theoretical computer scientist on my other hat, and it's to hear that they have a theory of mind, it's very difficult for me to understand why they call it theory.
Thank you so much. It was fascinating. Just one short question, something that was a bit baffling from that psychological or cognitive science perspective was seeing theory of mind defined as a behavioral prediction. Yeah, I understand that the notion of theory there is a legacy of a lot of thinking about what theorizing is, but I was wondering more in a trivial sense, some form of depth of reasoning or recursion usually comes about when we think about theory of mind. So I was just curious about that choice.
Well, we didn't try to look at the recursion of the things. And as I said, there are many open questions. I don't know, you know, and even a methodology how to check these things is very difficult. I can tell you, we've chosen 5 games. Are they the correct games? Can we do some recursion in the games? That's what I will do to check recursion. I will look at games that require this.
Thank you. We have one more question. No, can you?
Hi, thanks for the very interesting talk. Yeah, I was really curious about the negotiation stuff in particular because I'm interested in that topic as well. And you mentioned right now that the language models aren't very good in negotiation, but you also showed, I think, this graph that. So I'm kind of curious to hear more about the failure mode.
So I'll explain.
Yeah.
First, we just ask the LLM without any, just we giving a prompt. You are a mediator and you needs to have pre-negotiation interaction with one of the negotiators. Please interact and do something, okay? And this didn't work. It's not that you just can tell the LLM to do something, play the role of a mediator, and it will, by magic, be a good mediator. What I'm saying, that's what I said, you need to have a multi-agent LLMs, and actually I think you need also one that will do prediction, maybe one will do game theory model of the negotiation, and we suggest a strategy. So that's what I mean. They are just telling the LLM what to do, it doesn't work. I tried it.